Astronomers have discovered thousands of planets beyond our solar system, yet very few rocky worlds appear to have held on to their atmospheres. This matters because even a planet within the habitable zone may be little more than a cold, dry, barren sphere if its surrounding gases have been stripped away by its host star. LHS 1140b has drawn particular attention from scientists. Located nearly 49 light-years from Earth, this planet orbits a red dwarf star and may have endured a harsh environment for billions of years. But does it still have an atmosphere? Beneath that layer of gas, could there be rock, ice, or a vast ocean? And could a world like this truly be suitable for life? Welcome to Night Cosmos Sleep, where we explore the universe through a calm, unhurried rhythm that is easy to follow and gently absorbing. On tonight's journey, we will trace the faint clues hidden within light to better understand LHS 1140b, without rushing to call it a second Earth or treating unconfirmed possibilities as fact. The story begins at the moment this distant planet seemed to reveal its first breath. For a very brief moment, the light from a distant star dims ever so slightly. The change is far too subtle for the human eye to detect, but to instruments sensitive enough to measure it, the fading is a sign that something is passing in front of the star. That object is LHS 1140b, a planet nearly 49 light-years from Earth, so distant that the light we observe today began its journey almost half a century ago. No human has ever seen the planet's true surface. There are no images revealing its mountain ranges, plains, frozen seas, or horizon. Even through our most powerful telescopes, LHS 1140b appears too close to its host star in the sky to be separated into a clearly visible sphere. It exists in the data only through the tiny effects it has on the star's light. Each time the planet passes in front of the star, its dark body blocks a certain amount of light. But a planet is not a disk with a perfectly sharp edge. If an atmosphere surrounds it, the thin layer of gas along its outer rim allows some starlight to pass through before continuing toward Earth. That light does not emerge unchanged. As it travels through the atmosphere, certain wavelengths are absorbed by atoms and molecules. The resulting difference represents only a tiny fraction of the total light received, yet hidden within it is information about what surrounds a world humans cannot directly reach. In the case of LHS 1140b, the light carries the signature of helium. This is not the first time helium has been detected around an exoplanet. Astronomers have previously found the element escaping from many giant gas planets and from worlds orbiting extremely close to their stars. But LHS 1140b is different. It is a rocky planet within the habitable zone of a small star, where the amount of energy it receives could, in theory, allow liquid water to exist if the other conditions are also suitable. The detection of helium escaping from the upper atmosphere provides strong evidence that LHS 1140b truly retains a layer of gas around it. The importance of this discovery does not come from any connection between helium and life. Helium is not a sign that the planet has plants, microorganisms, or any other form of biology. It does not prove that breathable oxygen is present, nor does it confirm that an ocean lies beneath the atmosphere. Helium is simply a light element, and that very lightness makes it observable at extremely high altitudes. Sometimes, however, what matters is not the specific gas that has been detected, but what its presence allows us to infer. For helium to escape from a planet, helium must first exist around that planet. For the element to be present at high altitude, there must be an atmospheric system capable of carrying it upward. If this lightweight gas is still escaping today, then heavier gases may remain below it, more tightly bound to the planet, and beyond the direct reach of this observing method. Imagine LHS 1140b as a dark sphere surrounded by an exceedingly thin veil of vapor. From nearly 49 light-years away, the sphere itself is almost impossible to see, while the haze around it is even more elusive. Yet when starlight passes through that narrow rim, a few colors within the light are held back. We do not see the atmosphere itself. We see only the gaps it leaves behind. This is one of the strangest features of modern astronomy. We often study distant worlds not through what they emit, but through the light they remove. A dark planet can introduce itself by making its star grow dimmer. A transparent atmosphere can reveal its composition by preventing certain wavelengths from continuing their journey. Even an element escaping from a planet can become evidence that the world still retains part of a gaseous envelope that has endured for a very long time. The presence of helium, however, raises a question that seems almost contradictory. If gas is escaping into space, why is the detection considered so significant? Atmospheric escape is a natural process that occurs on many planets. An atmosphere is not an unchanging shell locked permanently to the surface. Its atoms are always in motion. Those in the upper atmosphere absorb energy from ultraviolet light, X-rays, and particles released by the star. As they heat up, they move faster, and some lightweight atoms can travel far enough that gravity can no longer pull them back. Even Earth does not retain its entire atmosphere forever. Small amounts of hydrogen and helium continuously leave the upper atmosphere and escape into space, but the process is extremely slow compared with the amount of gas that remains. Earth's atmosphere does not disappear simply because some atoms are leaving at every moment. In the same way, seeing helium escape from LHS 1140b does not mean its entire atmosphere is about to be swept away. It only shows that the upper atmosphere is interacting with energy from the star. The escaping gas can be imagined as vapor rising from the surface of a lake. Water vapor leaving the surface does not prove that the lake has dried up. On the contrary, it tells us that a source of water still exists below. Of course, a planetary atmosphere is far more complex than a lake, and helium is not produced or replenished in the same way as water vapor. But the image helps us understand the central point. Loss from the upper layers does not mean the entire system beneath them has disappeared. Models developed by the research team suggest that the upper atmosphere of LHS 1140b may be rich in helium but poor in hydrogen. Heavier gases may exist at lower altitudes, where gravity holds them more tightly and where the method used to detect helium cannot yet reveal their exact composition. This leaves a vast range of unanswered questions. Beneath the helium could be a thin, cold atmosphere that offers almost no protection to the surface. It could also be a denser layer of gas containing molecules, such as nitrogen or carbon dioxide. If water vapor is present, we do not yet know how much there is, where in the atmosphere it exists, or whether it is truly connected to liquid water on the surface. The current discovery opens only the first door. It does not allow us to step inside and see the entire world at once. But before that door opened, scientists could not even be certain that the planet had retained an atmosphere at all. Now, at least part of that question has been answered. To understand why this matters, we need to remember that planets orbiting red dwarfs may endure an extremely harsh youth. Red dwarfs are smaller and dimmer than the Sun, so the region receiving a moderate amount of heat lies much closer to the star. A planet with temperatures potentially suitable for liquid water must usually orbit at a relatively short distance. But that proximity also exposes it more strongly to ultraviolet radiation, X-rays, and stellar wind. When a red dwarf is young, it can be far more active than it is today. Powerful flares and high-energy radiation may heat a planet's atmosphere, break molecules apart, and drive some of the gas into space. Over hundreds of millions or billions of years, a small planet can lose much of its original atmosphere, leaving behind a surface that is dry, cold, or directly exposed to radiation. For this reason, we cannot simply assume that a rocky planet close to a red dwarf will still possess an atmosphere after such a long time. Before this discovery, we already knew that many rocky planets exist within habitable zones, but a favorable orbital position alone does not tell us whether their environments are suitable. A world without an atmosphere would struggle to distribute heat across its surface. The side facing the star could become far warmer than the dark side. Liquid water, if it ever existed, might freeze, evaporate, or be broken apart before gradually escaping into space. An atmosphere does not guarantee life, but it is often one of the important conditions that allow a planetary surface to maintain a stable environment. It can retain some heat, transport energy through moving air, create the pressure required for liquid water to exist, and reduce some of the effects of radiation. Its composition also participates in chemical cycles that may continue for millions or even billions of years. Yet every atmosphere is different. Venus has an atmosphere far denser than Earth's, but its surface is hot enough to melt lead. Mars still has an atmosphere, but it is too thin to sustain stable liquid water across most of the surface today. Titan has a thick atmosphere and lakes of liquid, but those liquids are composed mainly of methane and ethane in an environment far colder than Earth. The question, then, cannot end with whether LHS 1140b has an atmosphere. How thick is that atmosphere? What is it made of? Does it retain heat, or does it leave the planet frozen? Does it create enough pressure for liquid water? How has it changed over billions of years under the influence of its host star? Helium alone cannot answer any of these questions, but it gives us a firmer place to begin. It transforms LHS 1140b from a planet that may possess an atmosphere into a world whose upper atmosphere has left an observable trace. That trace is extraordinarily faint. If all the light received from the star were a brightly lit room, the change caused by helium might resemble only a passing shadow on the wall. To detect it, researchers had to observe at precisely the right moment as the planet crossed the star, separating the planet's signal from Earth's atmosphere, the motion of the star, and noise within the instruments. But once that signal was found, it carried a simple message. This world is not completely bare. Nearly 49 light-years away, a layer of gas still clings to a rocky planet. Some of its helium rises into the upper atmosphere, absorbs energy from the star, and slowly escapes the pull of gravity. Beneath that outflow lies an environment humans cannot yet see, but now have greater reason to keep searching for. It may be nothing more than a frozen sphere covered by a cold atmosphere. Its surface may be entirely rocky, or the planet may contain a great deal of water locked beneath a thick shell of ice or gathered in an ocean so deep that it resembles no ocean on Earth. Each possibility is fascinating, but none has been confirmed. That is the boundary we must preserve when speaking about distant worlds. Science does not fill empty spaces with what we hope to find. It begins with what the data allows us to see, then gradually eliminates explanations that do not fit. At present, the data indicates that helium is escaping from the upper atmosphere of LHS 1140b. This provides evidence that the planet still has an atmosphere, while the composition of its lower layers remains unknown. There is no evidence of trees, no sign of living organisms, and no image of blue seas. We do not even know whether an imaginary observer standing on the surface would see a bright sky, a dim haze, or a ceiling completely hidden by clouds. Even so, this discovery marks an important shift. For many years, the question was whether rocky planets beyond our solar system were common. Once thousands of exoplanets had been discovered, the question became which rocky worlds lie within habitable zones. Now, with LHS 1140b, the search is moving one step further. Among the planets orbiting at suitable distances, are there worlds that have truly retained their atmospheres long enough for their environments to have a chance to stabilize? For at least one planet, the answer now appears to be yes. That does not bring us all the way to life, but it brings the search closer to the conditions that life as we know it may require. LHS 1140b is not yet a second home. It is a question slowly coming into sharper focus. Each time the planet passes in front of its star, the light returns with another tiny part of the answer, not a complete image, but thin layers of information gathered over years of observation. Helium is the newest of those layers. It is escaping, yet that very escape reveals that something else is still being held. And before asking whether this planet supports life, we must first understand the world itself. How large is it? How massive is it? How much energy does it receive from its star? And why does a year there pass so much faster than a year on Earth? That will be the next step in our journey, because to understand the thin atmosphere that has just revealed the breadth of LHS 1140b, we must first understand what kind of planet is holding that atmosphere in place. Beneath the layer of helium, slowly escaping into space, lies a world that no human has ever seen directly. We do not know whether its surface is bright or dark, smooth or broken by mountain ranges and deep chasms. No image reveals its horizon, its clouds, or its true colors. Yet through years of observation, astronomers have assembled a preliminary portrait of its size, mass, orbit, and environment. These details do not form a complete picture, but they are enough to make LHS 1140b feel like a real place rather than simply a name in an astronomical catalog. LHS 1140b lies nearly 49 light-years from Earth. On the scale of the Milky Way, it is still considered a relatively nearby world. For humans, however, that distance is almost impossible to cross with current technology. Light travels faster than anything we can build, yet it still takes nearly half a century to reach Earth from the LHS 1140 system. What our telescopes see today is actually an image of that planetary system as it existed in the past. If a major change has just occurred there, the information about it is still traveling toward us. This distance places any direct visit far beyond our reach. No probe will arrive there anytime soon to measure temperatures, collect rock samples, or photograph the surface. Instead, we must study LHS 1140b by reading the light from its host star and observing the extremely subtle effects the planet creates. Every piece of information is inferred indirectly, much like trying to imagine a room using only the shadows and echoes that escape from within. The star orbited by LHS 1140b is a red dwarf. Smaller, cooler, and dimmer than the Sunday red dwarfs do not shine as brightly as our own star. Most of their energy is emitted in red and infrared wavelengths, making the environments around them significantly different from our solar system. Yet red dwarfs are also the most common type of star in the Milky Way. If planets around them can retain atmospheres and maintain stable conditions, the number of potentially interesting worlds in the galaxy would be far greater than we once imagined. But living close to a red dwarf is not easy. Because the star is small and dim, a planet must orbit much closer to receive a meaningful amount of warmth. That proximity may keep it from freezing completely, but it also exposes the planet more strongly to radiation, stellar winds, and powerful flares. These forces can heat the upper atmosphere, break molecules apart, and drive some of the gas into space. A planet orbiting a red dwarf is therefore caught in a constant struggle between receiving enough warmth and protecting the atmosphere around it. LHS 1140b is noticeably larger than Earth. Its radius is about 1.7 times that of our planet, while its mass is roughly 5 to 6 times greater. These measurements suggest that it is not simply an enlarged copy of Earth. Its size and mass allow for several possibilities regarding its internal structure. It may contain a metallic core, a thick rocky mantle, and a substantial amount of water. Much of that water may also be frozen or exist in unfamiliar states under extreme pressure. Its greater mass also means that gravity on the planet may be stronger. If there is a solid surface to stand on, the human body would feel heavier, and every movement would be more difficult than it is on Earth. But even the idea of a surface may not be simple. If LHS 1140b is rich in water, the rocky interior could be covered by an extremely deep ocean or by layers of ice so thick that no familiar dry land exists. When we say the planet is larger and heavier than Earth, we are describing only the dimensions of its outer form, not the full structure hidden beneath it. A year on, LHS 1140b lasts only about 25 Earth days. In other words, the planet completes one orbit around its star in less than one of our months. Yet a short year does not necessarily mean an excessively hot world. What matters is not only how close a planet is to its star, but also how much energy that star produces. The sun can be imagined as a large fire, powerful enough to warm Earth from a great distance. The star, LHS 1140, is more like a smaller glowing ember. A planet must move closer to feel its warmth. LHS 1140b can therefore orbit very near its star and complete each revolution quickly, while still receiving less energy than Earth does. Based only on the amount of starlight it receives, LHS 1140b appears to be a cold world. Its estimated equilibrium temperature lies well below the freezing point of water. However, That figure does not fully account for the effects of an atmosphere. A sufficiently thick layer of gas could retain heat, transport energy around the planet, and make some regions considerably warmer. If the atmosphere is too thin, however, most of the surface may remain covered in ice. Earth demonstrates how dramatically an atmosphere can alter a planet's temperature. Without the natural greenhouse effect, our world would be much colder, and its oceans would struggle to remain liquid as they do today. Gases such as water vapor and carbon dioxide trap some heat before it escapes into space. On LHS 1140b, the atmosphere's composition and thickness could determine the difference between a completely frozen sphere and a world with limited regions of liquid water. An atmosphere, however, does not always make an environment more favorable. Venus has an extremely dense atmosphere, but an overwhelming greenhouse effect has turned its surface into a place of extraordinary heat. Mars still has an atmosphere, yet it is too thin to retain enough warmth or sustain stable liquid water across most of the surface today. This shows that merely possessing an atmosphere is only the beginning. What matters more is what that atmosphere contains, how thick it is, and how it has changed over time. Because LHS 1140b orbits so close to its star, it may be tidally locked. This would mean that one side of the planet always faces the star, while the other remains in prolonged darkness. This has not been observed directly, but it is a reasonable possibility based on how gravity affects planets orbiting close to red dwarfs. If this scenario is correct, day and night on LHS 1140b would be very different from what we experience on Earth. On the day side, the star might appear almost motionless in the sky. On the night side, direct starlight would never appear at all. Between these two regions, there could be a transitional band where the star always remains close to the horizon, creating a realm of endless twilight. Without an atmosphere, the temperature difference between the two sides could be enormous. The day side would receive energy continuously, while the dark side would constantly lose heat to space. A sufficiently thick atmosphere, however, could generate winds that carry warmth from the illuminated hemisphere into the darkness. This circulation might soften the contrast and create more stable regions. The atmosphere discussed in the previous chapter therefore does more than show that the planet is not completely bare. It may also play a decisive role in determining how cold the surface of LHS 1140b becomes and in what state water might exist there. Another important detail is that the star LHS 1140 is currently relatively quiet compared with many other red dwarfs. This may help the planet avoid frequent powerful flares today. But the star was not necessarily always so calm. In its youth, it may have emitted much more high-energy radiation, placing intense pressure on the atmospheres of nearby planets. If LHS 1140b retained its atmosphere through that violent period, its mass and position may have helped it resist atmospheric loss more successfully than many other worlds. It may once have possessed a thicker atmosphere that gradually diminished over time. Geological activity within the planet may also have replenished the atmosphere with new gases. Its exact history remains unknown, but the escaping helium suggests that this process of evolution has not yet come to a complete stop. The same system also contains LHS 1140c, a smaller planet orbiting closer to the star. The two worlds may have formed from similar materials, yet their different sizes and distances would have exposed them to very different conditions. LHS 1140c receives more radiation and may have greater difficulty retaining an atmosphere. LHS 1140b, meanwhile, is larger, more distant, and held by stronger gravity, allowing it to preserve heavier gases more effectively. The contrast between these two planets resembles a natural experiment. They share the same star and the same planetary system, yet two different orbits and masses may have led them toward entirely different fates. One world may have gradually become bare, while the other retained its atmosphere for billions of years. Comparing them can help scientists better understand the boundary between a planet that still possesses an atmosphere and one whose protective gases have largely been stripped away by its star. The current portrait of LHS 1140b is therefore not built from any single measurement. It emerges from the combination of a planet larger than Earth, with strong gravity, orbiting a small and dim star, receiving a moderate amount of energy, and still retaining at least an upper atmosphere. Together, these characteristics make it an especially important target in the search for worlds with stable environments beyond our solar system. Still, we should not rush to turn these facts into an image of a second Earth. The light there is different from sunlight. A year is much shorter. Gravity may be stronger. The planet could be tidally locked, and much of its surface may be frozen. Even if water exists, it may lie beneath ice or within an ocean so deep that it bears little resemblance to the seas of Earth. What we can say is that LHS 1140b occupies a remarkable place between what is known and what remains uncertain. We know that it exists, that it is larger and more massive than Earth, that it orbits a red dwarf, and that at least part of its atmosphere is still present. But we do not yet know how thick that atmosphere is, what shape the surface takes, or whether water truly exists there in liquid form. Everything we know about this world has come not from a clear photograph, but from the moments when its star grows dimmer, from the tiny wobble caused by the planet's gravity, and from the way light changes as it passes through the gases along the planet's edge. Each measurement brings back only a small fragment, but when those fragments are placed together, a distant planet begins to acquire size, weight, an orbit, and an environment we can begin to imagine. LHS 1140b is no longer merely a dark point passing across its star. It is a world larger than Earth, moving swiftly around a faint red dwarf and perhaps concealing ice, water, or layers of rock beneath its atmosphere. But how can humans know any of this when we have never seen its surface? To answer that question, we must return to the moment the planet first appeared in telescope data, when a seemingly insignificant dip in starlight began to reveal the presence of an entirely new world. LHS 1140b was not discovered through a clear image. No one saw a distant sphere and realized that it was moving around a star. The planet revealed itself in a far more subtle way, through tiny changes in light. Each time it passed in front of its host star, the star's brightness decreased slightly, like a very small shadow crossing a source of light so distant that the human eye could never detect it. These dips in brightness did not occur at random. They repeated at a relatively steady rhythm. When the same decrease appears again and again, astronomers can begin to suspect that an object is orbiting the star. If the interval between each dimming remains nearly unchanged, that object may be a planet returning to the same position in its orbit. This method can be imagined as a dark room with a light bulb in the distance. If a person walks in front of the bulb, the light reaching our eyes briefly decreases. The larger the person, the more light they block. If they continue walking in a circle and repeatedly cross the same path, the shadow will appear at regular intervals. We do not need to see the person's face or clothing clearly to know that something is moving in front of the light. In astronomy, this search technique is known as the transit method. A planet passing in front of its star does not actually cause the star itself to grow dimmer. It simply blocks a portion of the light traveling toward Earth. The decrease can be so small that only extremely sensitive instruments are able to record it, but if the signal repeats enough times and retains the same shape, it can reveal far more than the planet's existence alone. The interval between two transits tells us how long the planet takes to complete one orbit around its star. The depth of the dip in brightness helps astronomers estimate the planet's relative size. A larger object blocks more light than a smaller one, just as an adult casts a larger shadow than a child when both pass in front of the same bulb. In reality, however, the process is more complicated than this simple image suggests. The star itself can change in brightness. Dark regions on its surface, stellar flares, and magnetic activity can create signals that may be mistaken for a planet. A distant binary star system can also produce periodic dimming as the two stars pass in front of one another. Even small errors within the instruments can leave traces that resemble a transit. For this reason, astronomers do not observe a single dip in brightness and immediately announce the discovery of a planet. They need to see the signal repeat, examine its shape, and compare it with other possible explanations. If the decrease in brightness is too deep, the passing object may be a small star rather than a planet. If the timing of the dimming is irregular, stellar activity may be responsible. Only after many alternative explanations have been ruled out does the signal become a reliable candidate. LHS 1140b was announced in 2017 after this kind of observing process. When astronomers recognized that the star was dimming at regular intervals, they knew that an object was orbiting it. The amount of blocked light showed that the object was larger than Earth, yet still far smaller than giant gas planets, such as Jupiter. It was soon placed in the category commonly known as super-Earths, a term used to describe planets that are larger or more massive than Earth, but smaller than Neptune-like worlds. The name can be misleading. A super-Earth is not necessarily a better version of Earth, a world richer in life, or even a planet that resembles Earth more closely. The term describes only a range of size and mass. A super-Earth may be a barren rocky sphere, an ocean world, an icy planet, or an object covered by a thick layer of gas. Size alone is not enough to distinguish between these possibilities. The transit method can reveal how large a planet is, but it does not directly tell us how much the planet weighs. Two planets of the same size may have very different internal structures. A world composed mainly of rock and metal will be heavier than one containing large amounts of water or gas, even if both block nearly the same amount of starlight. Imagine two balls of identical size. One is made of iron, while the other is made from a lightweight material and is hollow inside. When placed in front of a bulb, they cast the same shadow, but the difference becomes obvious the moment they are lifted. A transit tells us the size of the shadow, but another method is needed to determine the weight of the object. Astronomers do this by tracking the motion of the host star. A planet does not simply orbit a perfectly motionless star. Gravity acts in both directions. The star pulls the planet into orbit, but the planet also pulls back on the star. Because the star is far more massive, its movement is only a slight wobble. Even so, instruments precise enough can still detect it. Rather than saying that the planet orbits the exact center of the star, it is more accurate to say that both objects move around a shared point of balance. This point is known as the center of mass, or barycenter. When the planet is small and the star is large, the barycenter may lie deep inside the star. The star does not trace a wide circle across the sky, but it shifts slightly in one direction and then back again in rhythm with the planet's orbit. This motion is detected through extremely small changes in the star's light. When the star wobbles toward Earth, its light waves are compressed slightly. When it moves away, those wavelengths are stretched. The effect resembles the sound of a vehicle approaching and then receding. As the vehicle comes closer, its sound seems higher in pitch. After it passes and moves away, the pitch falls. With light, the change is not heard by the ear but measured with a spectrograph. This technique is commonly known as the radial velocity method. It reveals how quickly the star is moving toward us or away from us. From the strength of the wobble, scientists can infer the planet's gravitational pull and estimate its mass. The heavier the planet, the more noticeable its effect on the star. A small world produces a gentler wobble, while a massive planet can make the star move more strongly. Returning to the image of a person walking in front of a light bulb, the transit tells us how large the shadow is. But to understand how much the person weighs, we would need to feel how strongly the floor vibrates with each step. An adult and a child may block the light differently, but the shadow alone does not tell the entire story. When the darkness crossing the bulb is combined with the vibration moving through the floor, the person's form becomes clearer. This is also how the portrait of LHS 1140b was constructed. Its transits revealed its size and orbital period. The wobble of the star helped astronomers estimate its mass. By placing these two kinds of data together, researchers could calculate the planet's average density and begin to infer what may lie inside it. Density is a bridge between what can be observed and the hidden structure we cannot see. A planet with very high density is likely to contain mostly rock and metal. A lower density planet may hold more water, ice, or a substantial layer of gas. Yet density does not provide a single answer. Different internal structures can sometimes produce the same average value, so scientists must test multiple models and determine which ones best match the data. When LHS 1000 140b was first announced, the initial measurements made it appear to be an extremely dense rocky world. Its mass was estimated to be higher at the time, suggesting that the planet was composed mainly of rock and metal. This led many to imagine it as a larger, heavier, and colder version of Earth. But science does not stop with the first measurement. As more transits were recorded, more instruments monitored the star, and analytical methods improved, the portrait began to change. The estimated mass of LHS 1140b decreased. The planet remained larger and more massive than Earth, but its density was no longer as high as the early results had suggested. This change opened the door to another possibility. If the planet is not as dense as a sphere made entirely of rock and metal, it may contain a significant amount of lighter material. That material could be water in many different states, from liquid oceans to thick layers of high-pressure ice. It might also include an atmosphere composed of molecules heavier than hydrogen. This does not mean the earlier measurements were uselessly wrong. Each result reflected the amount of data and the level of precision available at the time. For a distant planet, the signal is extremely faint and mixed with many sources of noise, so early estimates often carry large uncertainties. As more observations are added, those uncertainties narrow, and the central value may shift. Science, then, is not the process of finding one number and preserving it unchanged forever. It is more like adjusting the focus of a camera. The first image may reveal only a blurred object. As the lens is refined and light is collected for longer, the outline gradually becomes clearer. Some details once thought certain may disappear, while new features begin to emerge. LHS 1140b is a clear example of this process. At first, it was pictured as an extremely dense rocky super-Earth. Later, more precise data allowed the possibility of a water-rich world to be considered more seriously. Even now, however, we cannot say that the planet has an ocean. Its mass and radius only show that such a possibility may be consistent with the data. They are not direct evidence of water on the surface. Many different structures can still produce the same size and mass. The planet may have a smaller iron core than Earth, but a thicker rocky mantle. It may contain water in its interior without having an open ocean at the surface. That water could be frozen or compressed into forms of ice that do not exist under ordinary conditions on Earth. An atmosphere could also make the observed radius larger than the solid body beneath it. Transit and radial velocity measurements, therefore, do not reveal the entire world. They only help construct the planet's basic framework. Transits show how much light it blocks, how long it takes to orbit its star, and how large it is. The star's wobble reveals how strongly the planet pulls on it, and therefore how massive the planet must be. By combining these measurements, researchers can narrow down the internal structures that may exist. This combination also helps eliminate many false interpretations. If a dimming signal is believed to come from a planet but the star wobbles too strongly, the passing object may actually be a small star. If no corresponding wobble is detected, the transit signal may come from another star system in the background. Each method checks the other, making the conclusion more reliable. Yet even when a planet's size and mass are measured reasonably well, one major question remains unanswered. Two planets with the same size and mass may possess completely different atmospheres. One world could be surrounded by a thick layer of hydrogen. Another might contain nitrogen, carbon dioxide, or water vapor. A third may have almost no atmosphere left at all. An ordinary transit reveals only the light blocked by the body of the planet. To search for an atmosphere, astronomers must examine changes that are far smaller and occur along the planet's edge. As starlight passes through the surrounding gas, certain colors are absorbed more strongly than others. These differences are much smaller than the amount of light blocked by the planet itself, but they contain information about the atoms and molecules that are present. The body of the planet can be imagined as a closed door standing in front of a light bulb, while the atmosphere is like a thin curtain around its edges. The door blocks nearly all the light behind it. The curtain allows light to pass through, but changes its colors. To learn how large the planet is, we only need to measure the darkness created by the door. To discover what the atmosphere contains, we must study the subtle changes in the light that has passed through the curtain. This is a far more difficult step. The atmospheric signal may be so faint that it is hidden by stellar activity, water vapor in Earth's atmosphere, or noise from the instruments. Researchers must observe at precisely the moment the planet transits, compare the light before, during, and after the event, and then remove any signatures that do not belong to the planet. For LHS 1140b, transits allowed humans to find the planet and estimate its size. The wobble of the star helped determine its mass and opened the possibility that this world contains more lightweight material than rock alone. But to learn what surrounds it, astronomers had to look more deeply into the same starlight, searching for the tiny gaps left behind by individual atoms. The planet was discovered as its star grew dimmer. Its mass was revealed through the star's almost imperceptible motion. Now the question is no longer only how large and heavy that sphere may be. The next answer lies within the thin layer of light that has passed through the planet's edge. Size and mass can tell us what LHS 1140b may be made of. But to understand what surrounds it, humans must read changes in the star's light that are far smaller still. After determining the size, mass, and orbit of LHS 1140b, astronomers still did not know what the layer of gas surrounding the planet actually contained. Earlier measurements had only helped construct the basic framework of this distant world. To go further, they needed to observe the tiny fraction of starlight passing through the edge of its atmosphere as the planet moved across the face of its host star. The solid body of LHS 1140b blocks the starlight almost completely, but its atmosphere does not end at a hard boundary. At higher altitudes, the gas becomes increasingly thin and gradually fades into space. Starlight can still pass through this tenuous region before continuing toward Earth. During that brief passage, some of the light is absorbed by atoms and molecules, leaving extremely subtle traces in the spectrum. Starlight can be imagined as a piece of music composed of countless notes. As the music passes through a planet's atmosphere, a few of those notes become weaker. Astronomers do not see helium as a clearly defined cloud. They only notice that one very narrow region of the light becomes dimmer while the planet is passing in front of the star. Each type of gas interacts with light in its own way. Oxygen, water vapor, carbon dioxide, and helium all leave different absorption signatures. These are like fingerprints, not because the atoms have visible shapes, but because each kind absorbs only certain portions of the light. When the positions of those missing wavelengths match the known signature of helium, researchers have reason to suspect that the element is present in the upper atmosphere. On LHS 1140b, helium was searched for in the near-infrared, where a special state of the atom can produce a more noticeable absorption signature. This state is commonly called metastable helium. The name may sound complicated, but the essential idea is simple. A helium atom can remain in this energy state long enough to interact with light and leave a trace that observing instruments can detect. That trace is extraordinarily small. Compared with the amount of light blocked by the body of the planet, the atmospheric signal is only a very thin haze around the edge. The planet can be imagined as a black disk moving across a lamp, while its atmosphere resembles an almost transparent veil surrounding the disk. The main shadow is relatively easy to detect, but the veil changes the light only slightly. The entire search depends on distinguishing that tiny change from countless other sources of interference. Light from LHS 1140 does not enter the instrument through a perfectly clean environment. Before reaching the telescope, it must also pass through Earth's atmosphere. Water vapor, oxygen, and many other molecules around us leave their own absorption signatures in the near-infrared. Some of the traces produced by Earth's atmosphere are far stronger than the signal from the planet. The host star is not perfectly stable either. Active regions on its surface, the motion of hot gas, and magnetic fields can all alter its spectrum. For this reason, a dark line appearing at the expected position of helium is not enough by itself. The research team had to determine when the signal appeared, how it changed, and whether it truly moved with the planet. A signature from Earth's atmosphere would follow Earth's motion. A signal belonging to the star would move with the star. But the atmosphere of LHS 1140b should carry the planet's own velocity as it crosses in front of the light source. This is what makes the observation resemble an investigation. Many different sources leave traces in the data, and each one carries its own motion. Scientists must follow the helium signal from one moment to the next, much like separating a single voice from a crowd by recognizing the direction in which that person is moving. Imagine someone walking across a room while many others remain still and speak at the same time. The moving person's voice changes very slightly as they approach and then move away. By knowing the path that person is taking, we can follow those changes and separate the voice from the surrounding noise. Astronomers apply a similar principle to light. The helium signature becomes convincing only when it shifts at the velocity expected for LHS 1140b. These observations were made with WINERID, a spectrograph designed to study near-infrared light. Mounted on the Magellan Clay Telescope at Las Campanas Observatory in Chile, the region offers dark skies, dry air, and favorable conditions for reducing interference from water vapor in Earth's atmosphere. The telescope collects the extremely faint light that has crossed nearly half a century of space, while WINERID divides that light into narrow components to search for the characteristic absorption signature. The helium detection did not come directly from the James Webb Space Telescope. James Webb has carried out other important observations of LHS 1140b, particularly in testing models of a thick, hydrogen-rich atmosphere. The helium signature in the upper atmosphere, however, was found using the instrument mounted on the Magellan Clay Telescope. These two kinds of observations do not contradict each other. Instead, they complement one another. James Webb helps test what may exist in the deeper layers of the atmosphere, while WINERID focuses on the much higher region where the gas becomes thin, heats up, and begins to expand away from the planet. One instrument examines the deeper atmosphere, while the other follows the boundary where it comes into direct contact with space. When the results are combined, the atmosphere no longer appears as a simple shell, but as a multi-layered system in which each region experiences different conditions. Before detecting the signal, the research team developed models of how the upper atmosphere of LHS 1140b might behave. The planet may once have possessed more lightweight gases during its early history. Hydrogen would have escaped more quickly, while helium may have been lost somewhat more slowly and remained present at high altitudes. Radiation from the star continues to heat this gas, causing it to expand and allowing helium to leave a signature in the light passing through it. The observations then revealed an absorption feature exactly where helium was predicted to appear. The signal grew stronger during the planetary transit and shifted with the velocity of LHS 1140b. It did not remain fixed like signatures produced by Earth's atmosphere, nor did it match a simple variation in the star. Several details pointed toward the same explanation. Helium is present in the planet's upper atmosphere. This was not a moment when humans photographed a cloud of gas rising from the surface. There was no clearly visible stream of light trailing behind the planet. All the instrument recorded was a region of light slightly weaker than expected. Yet from that subtle change, scientists could infer that the absorbing gas lies above the planet's main body and extends outward into space. In the lower atmosphere, gas is held more tightly by gravity. At higher altitudes, the density decreases, and atoms can absorb energy more directly from ultraviolet light, X-rays, and particles released by the star. The helium becomes heated, moves faster, and gradually reaches a region where gravity is no longer strong enough to pull every atom back toward the planet. This process unfolds slowly and continuously. The gas is not blasted away from the planet in a single eruption. Individual atoms escape over an immense span of time, forming an extremely tenuous region of gas around the world. Stellar wind may pull this material in one direction, shaping it into a faint tail that no human eye could see. From Earth, we recognize the gas only through the portions of starlight it absorbs. The fact that helium is escaping does not mean the entire atmosphere is about to disappear. Earth also continuously loses small amounts of lightweight gas into space, yet it has maintained its atmosphere for a very long time. To understand how quickly LHS 1140b is losing gas, scientists would need to know how much atmosphere remains, the rate at which it escapes, and whether material from deeper layers can replenish it. The current signal mainly shows that atmospheric loss is taking place. By itself, it cannot reveal the planet's entire history. The helium may also have more than one possible origin. Some of it could be material left over from the planet's formation. Another portion may be produced within the planet through the slow radioactive decay of elements in its rocks before rising into the atmosphere. On Earth, helium created underground can travel upward through cracks and eventually escape into space. LHS 140b may undergo a similar process, although there is not yet enough data to determine which source plays the dominant role. What is more certain is that the planet's atmosphere is not a motionless shell. Material is moving upward from below, absorbing energy from the star, and gradually escaping into space. Helium therefore reveals not only a component of the atmosphere, but also an active process. The planet is interacting with its host star, and its upper atmosphere is responding continuously to the surrounding environment. This is especially important for a world orbiting a red dwarf. Small stars may pass through highly active stages in their youth, releasing intense high-energy radiation that erodes the atmospheres of nearby planets. LHS 140b does not appear to have lost its gaseous envelope completely. Although some of its lighter gases have escaped, enough material remains at high altitude to leave a detectable signature in the starlight. One observation, however, is not enough to describe the entire system. The atmosphere may change with the activity of the star, the direction of the stellar wind, or the thermal state of the upper layers. The research team therefore continued observing additional transits to see whether the helium signature would repeat in the same way. The results did not produce an entirely simple story. During one observation, the helium signal appeared clearly enough to be tracked. During the next, the same region of the spectrum became much weaker. This difference does not mean the atmosphere had vanished, but it suggests that the upper gas may be changing, or that the shape of the helium region does not remain constant over time. The gas cloud may be pushed away from our line of sight by the stellar wind. The upper atmosphere may contract when it receives less energy or expand when the star becomes more active. The density of helium in the special absorbing state may not be the same during every transit. Instrumental noise and interference from Earth's atmosphere also remain factors that must be examined carefully. This variation makes LHS 140b appear more dynamic within the data. Rather than forming a fixed layer, the upper atmosphere may swell, contract, or stretch outward depending on the state of the star. Each time the planet passes in front of its light source, the transit becomes a separate frame, capturing a different stage of the same ongoing process. Helium does not appear as a glowing cloud around LHS 140b. It reveals itself only through a few weakened notes in the star's music of light. At times, those notes are clear enough for researchers to follow the planet's motion. At others, they nearly fade into silence. That variation leads to the next question. Why can an atmospheric signature appear clearly during one observation, yet become faint and elusive during another? During the first observation, helium left an absorption signature clear enough for researchers to trace the motion of LHS 140b. But when the planet crossed in front of its star again during a later observation, the same signature was no longer clearly visible. The same planet, the same star, and the same region of light were being studied, yet the data told two different stories. One observation revealed gas expanding and escaping from the planet, while the other returned almost nothing but silence. The study interprets this difference as a sign that atmospheric escape may vary over time rather than continuing at the same intensity during every transit. That silence does not mean the atmosphere disappeared during the relatively short interval between the two observations. Based on the available data, a layer of gas surrounding the planet could not appear and then vanish completely so quickly. Nor does it automatically prove that the original signal was incorrect. The research team reprocessed both datasets using an independent method and still found the same difference. The unresolved question is not which observation was right and which was wrong, but what made helium easy to detect on one occasion and caused it to fall below the limit of observation on another. An atmosphere is often imagined as a motionless shell surrounding a planet, but in reality, it is always moving. The lower layers contain winds, clouds, and circulation patterns that transport heat from one region to another. Higher above, where the gas becomes extremely thin, the atmosphere responds directly to radiation and charged particles from the star. This region can heat up, expand, contract, or stretch in the direction of the stellar wind. Helium exists within this highly changeable environment, so its absorption signature does not necessarily remain the same from one transit to the next. The process can be imagined as smoke rising from a chimney. The house remains in the same place, and the chimney itself does not change, but the shape of the smoke is rarely identical from one moment to another. When the air is still, the smoke may rise in a relatively distinct column. A crosswind can pull it into a long trail. Stronger winds may tear the smoke into smaller patches and scatter it so quickly that it becomes almost invisible from a distance. The absence of a clearly defined plume does not mean the house has disappeared or the chimney has stopped working. It simply means the material is being distributed differently. The helium surrounding LHS 1140b may behave in a similar way, although the environment there is far more complex. Gas escaping from the planet does not necessarily form an even spherical layer. The stellar wind may push it toward one side, creating an extended region of gas ahead of or behind the planet along its orbit. During the observation in which the signal appeared clearly, the data also suggested that helium was present before the body of the planet began crossing the star. This is consistent with the possibility that some of the gas had stretched forward, forming something like a reverse tail or a stream of material shaped by the interaction between the planet and the environment around its star. The shape of the outflow determines how much helium lies along the path of the starlight. If an extended cloud happens to cross the face of the star, the light must pass through more atoms, producing a stronger absorption signature. If the gas is pushed above, below, or to one side of our line of sight from Earth, less helium remains in front of the stellar disk. The gas may continue escaping, but the instrument no longer looks through its densest region. The absorption signal then becomes fainter, sometimes weak enough to blend into the noise. This is an important limitation of the transit method. A telescope does not observe the entire atmosphere from every direction. It probes only the gas that happens to lie between the star and Earth during the few hours when the planet passes in front. Each transit is like a thin slice through a moving system. One slice may pass through a dense region of gas, while the next barely touches a thinner area. Changes in the data, therefore, do not necessarily reflect the disappearance of the atmosphere. They may instead reveal that the outflow has changed its shape or position. Along with geometry, the amount of energy coming from the star may also vary. The upper atmosphere is heated mainly by X-rays and high-energy ultraviolet radiation. These forms of light are invisible to the human eye, but they can transfer enough energy to make the gas expand and drive atmospheric escape. When the radiation increases, helium at high altitudes receives more energy, the atmosphere may swell outward, and the density within the observed region may change. When the star enters a quieter state, the upper atmosphere may contract or produce fewer helium atoms in the particular absorbing state required for detection. Importantly, the helium signature does not depend only on the total amount of helium present. The atoms must occupy a special energy state to strongly absorb the wavelengths monitored by Weinert. The number of atoms in this state is influenced by temperature, ionization levels, and the spectrum of radiation emitted by the star. An atmosphere containing nearly the same amount of helium can still produce signals of very different strengths because only part of that helium is in the correct state to be detected. This can be compared to a room filled with people where only those holding lamps are visible in the darkness. The number of people in the room may not change, but the number of lamps that are switched on can rise or fall. From outside, the room may appear brightly illuminated at one moment and much darker at another, even though the people remain inside. In the case of helium, radiation from the star and conditions in the upper atmosphere determine how many atoms can leave an absorption signature in the light. The research team's models show that moderate changes in high-energy radiation or in the temperature of the outflow could reduce the helium signal below the sensitivity of the later observation. This would not require atmospheric escape to stop completely. The outflow would only need to become weaker, grow hotter in a way that makes the absorption line broader and shallower, or contain less metastable helium for the instrument to lose a clear view of it. At first, the idea that higher temperatures could make the signal harder to detect may seem contradictory. Hotter gas often expands more strongly, so it is natural to assume that the absorption should become more obvious. But when atoms move across a wider range of velocities, the spectral signature can spread out. Instead of forming a narrow, deep line, the signal becomes broader and shallower. The total amount of gas may not be lower, but the contrast at each wavelength decreases, making it more difficult to separate from the noise. The stellar wind is also not a steady stream flowing evenly past the planet. It is a current of charged particles moving outward from the star, and its density, speed, and direction can all change. When this flow collides with the upper atmosphere, it may compress one side, stretch the other, or carry material along complex curved paths. The star's magnetic field, along with the planet's own magnetic field if LHS 1140b possesses a significant one, may guide the escaping gas in still other directions. We do not yet know whether LHS 1140b has a strong magnetic field. No direct measurement has revealed whether a metallic core inside the planet is generating a protective magnetic shield like Earth's. Even so, electromagnetic interactions remain a possibility that must be considered when explaining the shape of the helium outflow. A stream of gas extending ahead of the planet, as the detection appeared to suggest, could be related to the stellar wind or to the way the magnetic fields of the two bodies connect. For now, however, this remains an interpretation rather than something directly observed. The plasma environment around the star makes the story even more complex. Plasma is a state of matter in which many atoms have lost electrons, creating a mixture of electrically charged particles. It responds more strongly to magnetic fields than neutral gas and can form flows, waves, and compressed regions that are extremely difficult to predict. The upper atmosphere of LHS 1140b lies precisely where neutral gas, radiation, plasma, and gravity meet. Even a small change in one component could alter the entire structure of the outflow. The difference between the two observations therefore does not necessarily have a single cause. Stellar activity may have changed the temperature and energy state of the helium, while the stellar wind simultaneously bent the outflow in another direction. From Earth's viewing angle, the densest portion may no longer have crossed the stellar disk. Finally, the instrument's limitations may have allowed the weakened signal to sink below the level at which it could be distinguished. Several small effects acting together can sometimes produce two data sets that appear completely different. It is also important to remember that every ground-based observation must pass through our own atmosphere. Humidity, air movement, and the position of the star in the sky all change throughout the night. Researchers have many methods for correcting these effects, but no measurement is ever entirely free of noise. An extremely faint signal may appear more clearly under favorable conditions and become much harder to identify when the data is less stable. Instrument sensitivity creates a boundary between something that is not detected and something that does not exist. These are not the same. When a boat disappears into fog, we can only say that it is no longer visible. We cannot conclude that it has left the water. In the same way, helium falling below the detection threshold means only that its absorption signature was too weak compared with the noise during that observation. Scientific research preserves this distinction very carefully. Not detected does not mean not present. To claim that an atmosphere had disappeared would require far stronger evidence, along with a sequence of observations showing every signal declining in a manner consistent with complete atmospheric loss. For LHS 1140b, the current data is more consistent with a changing upper atmosphere that sometimes produces a strong enough signal and at other times becomes difficult to detect. This variability does not make the discovery any less interesting. On the contrary, it suggests that humans may be observing a dynamic process rather than a motionless layer of gas. Each time the planet passes in front of its star, it is like a frame captured at a different moment in an extremely slow film. One frame shows the helium outflow clearly expanded. The next shows the structure fading. Only after more frames are collected will scientists be able to recognize the true rhythm of the upper atmosphere. Earth also has an upper atmosphere that changes continuously in response to solar activity. Powerful eruptions heat this region and cause it to expand. The density at satellite altitudes increases, exposing spacecraft to greater drag. Geomagnetic storms can expand the auroras and disrupt communication systems. When the sun becomes quiet again, the upper atmosphere contracts. Most people on the ground do not directly feel these changes, but instruments in space can measure them clearly. This comparison does not mean that the atmosphere of LHS 1140b resembles Earth's. Its composition, temperature, and level of radiation may all be very different. It does remind us, however, that the upper atmosphere of a planet is not a fixed boundary. It responds to its star almost immediately on astronomical timescales. A signal that changes between observations is therefore not especially difficult to understand, even though the precise mechanism still requires more data. Helium is a lightweight element, allowing it to reach higher altitudes more easily than heavier molecules. There, the atoms absorb energy, move faster, and some eventually overcome the planet's gravitational pull. This general process is known as atmospheric escape. It can occur in several ways, from individual atoms leaving one by one to an entire heated flow of gas streaming outward like a planetary wind. In the case of LHS 1140b, the research team interprets the signal as atmospheric outflow driven by high-energy radiation from the host star. Gas in the upper layers becomes hot enough to expand and flow outward. This is not a wind blowing across the surface, but matter moving from the planet into space at extremely high altitudes. The model also suggests that the outflow contains little hydrogen compared with helium, consistent with the possibility that the lighter hydrogen was lost more extensively in the past. Yet observing helium escape does not mean that LHS 1140b is about to become a barren sphere. Every planet with an atmosphere loses some material over time. Earth continuously allows hydrogen and helium to escape from its upper atmosphere. Mars also loses gas under the influence of the solar wind. Even the giant gas planets have atoms at their outermost edges that drift away into space. What determines the long-term fate of an atmosphere is not simply whether gas is being lost, but how quickly that loss occurs compared with the amount that remains. A small tank leaking at the same rate as a vast lake will face a very different outcome. To know how long LHS 1140b can maintain its atmosphere, scientists must determine the total mass of its gases, the radiation history of the star, the current escape rate, and any sources of replenishment from the planet's interior. The available data cannot yet answer all of these questions. The helium signal provides a snapshot of atmospheric escape in the present, but it does not tell the entire history. The star may have been much more active in its youth, causing gas to escape at a far greater rate. As the star grew quieter, the erosion may have slowed. The atmosphere observed today could be what remains after billions of years of change. A layer of heavier gas may lie below, held tightly by the planet's strong gravity. Elements such as oxygen, carbon, and nitrogen are more difficult to carry away with the helium flow. Water may also remain trapped in the lower atmosphere because the cold temperatures cause its vapor to condense before it can reach the region where gas escapes. In this way, LHS 1140b may lose its lighter components while preserving much of the heavier material beneath them. Over time, this could create a stratified atmosphere. This helps explain the paradox at the heart of the discovery. Helium is leaving the planet, yet the fact that we can detect it shows that an atmosphere large enough to supply the upper layers still exists. A world with no gas at all could not produce a helium outflow. A planet that had lost its entire gaseous envelope long ago could not leave an extended absorption signature across the face of its star. Imagine a river flowing into the sea. Water is leaving the land, but the current shows that a system upstream is still supplying it. Observing the river's mouth alone cannot reveal how large the reservoir is or how long the rainfall will continue, but it proves that water is still being transported. The helium around LHS 1140b is similar, a sign at the boundary between the atmosphere and space. The variation between the two observations therefore does not diminish the value of the first signal. It shows that the outflow is uneven, as many natural systems are. At times, the atmosphere expands and lies directly along the path of the starlight. At others, it contracts, disperses, or is pushed aside. Each state reveals a different part of the way the planet responds to its star. Future transits will be crucial. As the number of observations increases, scientists can compare the strength of the helium signal with X-ray activity, ultraviolet radiation, and the changing state of the star. They can also search for signs of extended gas tails, determine whether those structures usually stretch ahead of or behind the planet, and see whether the silence appears again. A long sequence of data will transform two isolated moments into a pattern of motion that can be understood. For now, the most cautious interpretation is that the upper atmosphere of LHS 1140b is changing. Helium appeared clearly during one observation, but did not rise above the detection threshold during the next. The difference may have resulted from the star's radiation level, the temperature of the outflow, the shape of the helium tail, or some combination of these factors. Limits in sensitivity still prevent many of these possibilities from being fully distinguished. Behind that uncertainty lies an even more remarkable conclusion. The atmosphere of a distant world is no longer merely an idea within a model. Humans have begun to observe how its outermost layers respond to the star, even if only through a few faint traces in the light. A signal that brightens and fades is not the voice of a dead system. It resembles the changing rhythm of a gaseous layer being heated, stretched, and slowly blended into space. Helium is still escaping from LHS 1140b, but before it could escape, it had to be retained. For an outflow to remain after such a long history beneath the light of a red dwarf, the planet must have resisted erosion more successfully than many other rocky worlds. The loss we observe today therefore becomes evidence that LHS 1140b has not lost everything. The paradox remains. Helium is escaping from the planet, yet the trace of that departure shows that this world has retained an atmosphere for a very long time. To understand how it managed to do so, we must look more deeply into the unending struggle between the planet's gravity and the energy released by its star. A planet's atmosphere is not a shell permanently locked around its surface. It exists in a constantly shifting balance, with gravity trying to hold molecules close while heat, radiation, and stellar wind continually work to drive them away. Every planet is caught in this struggle, but the outcome is not always the same. Some worlds retain thick atmospheres for billions of years, others are left with only a thin layer of gas, and some planets have become almost completely bare, leaving their surfaces directly exposed to space. Gravity is the force that pulls everything toward the center of a planet. The more massive a world is, the more strongly it can usually hold on to its gases. For molecules to escape, they must move fast enough to overcome that pull. This is easier for lightweight gases such as hydrogen and helium. Heavier molecules generally move more slowly at the same temperature, making it more difficult for them to leave the planet. Mass, however, is not the only factor. Even a large planet can lose gas quickly if it becomes too hot. Higher temperatures cause atoms to move more rapidly. In the upper atmosphere, some may reach speeds great enough to escape without returning. Radiation from the star can also break molecules apart, creating lighter components that are more easily lost. The atmosphere can be imagined as a crowd standing inside a valley. Gravity forms the surrounding slopes that keep everyone within it. Heat and radiation provide the energy needed to climb upward. Those who are lighter, faster, and receive more energy are more likely to cross the ridge. Heavier individuals tend to remain below. Over immense periods of time, the valley may gradually lose its lighter occupants while retaining the heavier ones. LHS 1140b has a clear advantage in this struggle. It is more massive than Earth and has stronger gravity. This allows it to hold on to gas more effectively than many smaller rocky worlds. An atom moving through the upper atmosphere must reach a higher speed to escape completely. Gravity cannot prevent every loss, but it can slow the process. Even so, the planet orbits close to a red dwarf. That distance allows it to receive enough warmth to avoid becoming entirely frozen, but it also places the upper atmosphere closer to a powerful source of radiation. Red dwarfs are small and faint in visible light, yet they can emit significant amounts of ultraviolet radiation, X-rays, and charged particles, especially during the early stages of their lives. A young star does not shine as steadily as a light bulb. Its surface contains powerful magnetic fields, active regions, and sudden flares. During a flare, the amount of high-energy radiation can increase rapidly. Such events heat the upper atmosphere, causing it to expand and making it easier for matter to escape into space. Stellar wind also contributes to atmospheric erosion. This is not wind like the kind found on Earth, but a continuous stream of charged particles flowing outward from the star. When these particles collide with a planet's atmosphere, they can transfer energy, push ions, and carry material away. A world with a strong magnetic field may deflect part of the stellar wind, but a magnetic field is not a perfect shield. In some cases, it can guide particles toward the polar regions, where they interact with the atmosphere. We do not yet know whether LHS 1140b has a global magnetic field. To generate one like Earth's, a planet generally needs electrically conductive material moving within its interior, such as a hot, convecting metallic core. Its large size may allow it to retain internal heat for longer, but the true structure of LHS 1140b remains uncertain. It may contain a metallic core, a thick, rocky mantle, a large amount of water, or some combination of these components. Whether or not it has a magnetic field, the planet's gravity remains an important form of protection. It helps keep heavier molecules in the lower atmosphere even as lighter components are gradually lost. Over billions of years, this process may have changed the atmosphere considerably from its original state. A gaseous envelope once rich in hydrogen may have become depleted in hydrogen, while helium and heavier molecules grew more dominant. The upper atmosphere of LHS 1140b is currently thought to be rich in helium but poor in hydrogen. This arrangement is not especially surprising. Hydrogen is lighter than helium and is therefore more easily lost. During the star's highly active youth, hydrogen may have escaped rapidly, carrying some helium with it. As the radiation gradually declined and the planet entered a more stable period, the remaining gases continued to separate according to their mass. Molecules such as nitrogen, carbon dioxide, and water vapor are considerably heavier. They have greater difficulty reaching high altitudes and are less likely to achieve escape velocity. Water vapor may also condense in colder layers, forming clouds, ice, or liquid water before it can reach the region where intense radiation might split it into hydrogen and oxygen. The loss of helium therefore does not mean that heavier components are escaping at the same rate. An atmosphere can be imagined as a multi-story building. On the highest floor, lightweight gases are more common and are directly exposed to radiation. Below are denser layers, where pressure rises, temperatures change, and heavier molecules become dominant. Finding helium on the roof does not reveal what is inside the rooms below, but it does show that the building has not disappeared. The age of the host star makes the story even more significant. LHS 1140 is currently relatively quiet compared with many highly active red dwarfs. That does not mean it never passed through a violent period. In its youth, the star may have emitted far more ultraviolet radiation and X-rays than it does today. LHS 1140b had to endure that stage while its atmosphere was still developing and its surface was continuing to change. During those early periods, the primordial atmosphere may have been heated intensely. Hydrogen would have escaped first, with helium following more slowly. Any oceans that existed early in the planet's history may also have been affected. Water vapor carried into the upper atmosphere could have been split by radiation into hydrogen and oxygen. The lightweight hydrogen would escape into space, while the oxygen might remain behind, react with rocks, or accumulate in the atmosphere. This process shows how profoundly a planet can change without experiencing a single catastrophic event. A small amount of gas escaping continuously over a sufficiently long time can leave the final composition entirely different from the original one. A thick hydrogen envelope may gradually become thinner. Some water may be lost. The surface and atmosphere exchange material, while volcanoes and other geological processes release new gases from the planet's interior. The atmosphere we see today is therefore the product of an entire history. It does not depend only on how much gas the planet received when it formed. Impacts can add material or strip it away. Volcanoes can release carbon dioxide, water vapor, and nitrogen to the surface. Rocks can absorb certain gases and later release them again. Ice can trap water in cold regions and free it when temperatures change. Above all of this, the star is constantly removing a small portion of the atmosphere. The struggle does not involve only two opposing forces. Gravity pulls downward, the star drives material outward, and the planet's interior may replenish the gases that have been lost. The balance among these three processes determines whether an atmosphere grows, declines, or remains relatively stable over long periods of time. A planet with strong geological activity may replace some of the gas it loses. Volcanoes and fractures can carry material from the mantle into the atmosphere. By contrast, a world that has cooled completely would have far less ability to supply new gases. As its internal sources weaken, every loss from the upper atmosphere becomes more difficult to replace. Because LHS 1140b is larger than Earth, it may be able to retain internal heat for longer, but this is not enough to confirm that it still has active volcanoes or tectonic processes. Greater size slows the cooling process, yet the amount of water, the structure of the core, and the composition of the rocks can all affect how heat moves through the planet. A deep ocean or layers of high-pressure ice could also isolate the interior from the atmosphere. Although the level of geological activity remains unknown, the presence of helium raises the possibility of replenishment from deep below. Helium can be produced through the radioactive decay of elements within rocks. On Earth, some of this helium rises through the crust and enters the atmosphere. LHS 1140b may experience a similar process. Whether enough helium is being produced to balance the escaping flow remains an open question. When scientists compare many planets, they find that the ability to retain an atmosphere does not vary randomly. Small, hot worlds tend to lose their gases more easily. Larger or colder planets are generally more likely to preserve thick atmospheres. From this relationship comes a concept often called the cosmic shoreline. The name suggests a boundary between land and water, but no sharp dividing line like that exists in space. The cosmic shoreline is a way of describing a general trend. On one side are planets with gravity strong enough, temperatures low enough, or stellar environments calm enough to retain their atmospheres. On the other are worlds more vulnerable to losing their gases through heat and radiation. This boundary is not fixed. Atmospheric composition, magnetic fields, stellar age, and geological activity can all push a planet toward one side or the other. Two worlds of the same size may meet very different fates if they orbit different stars. A planet close to an active star faces a greater challenge than one receiving the same amount of warmth from a quieter star. Within the LHS 1140 system itself, there is an especially useful comparison. LHS 1140c lies closer to the star, is smaller, and receives more radiation than LHS 1140b. Although both orbit the same star, the two planets have faced different conditions since the time they formed. Planet C lies deeper within the region most strongly influenced by the star. Greater heat and radiation make its upper atmosphere more likely to expand. Its weaker gravity also means that atoms require less energy to escape. Over long periods, this combination may remove far more gas than it does from Planet B. Observations have not revealed a clear helium signature around LHS 1140c. This does not prove that the planet has no atmosphere at all. The signal may be too weak, the atmospheric composition may be different, or the helium may have been lost long ago. Even so, the contrast with LHS 1140b is consistent with the idea that the two planets occupy different positions relative to the cosmic shoreline. LHS 1140c may have lost most of its lightweight gases early in its history. It may also retain a thin atmosphere composed of heavier molecules but no longer have enough helium at high altitude to produce a clear absorption signature. LHS 1140b, meanwhile, is larger, colder, and farther from the star, helping it preserve a richer atmospheric system. The two worlds can be imagined as stones placed at different distances from a fire, The smaller stone closer to the flames heats more quickly and loses its volatile materials more easily. The larger stone farther away retains heat differently and experiences a gentler effect. But planets are not passive objects. They have interiors, atmospheres, perhaps water, and geological processes that continue over immense periods. The final outcome is therefore always more complex than the simple comparison suggests. The difference between two planets in the same system is especially valuable because they share many initial conditions. Both formed from the disk of material surrounding the same star and experienced a similar history of stellar radiation. Their distance, size, and internal structure become the most important variables. This allows scientists to examine the roles of gravity and incoming energy without comparing two completely unrelated systems. LHS 1140b appears to have resisted atmospheric erosion more successfully than its inner neighbor. Its stronger gravity keeps gas closer to the planet. Its lower temperature causes atoms to move more slowly. Its greater distance reduces some of the effects of radiation and stellar wind. Small advantages like these, accumulated over immense spans of time, may create the difference between a world that still has an atmosphere and one left with only a very thin layer of gas. Retaining an atmosphere, however, does not necessarily mean preserving a favorable environment. Venus has kept an extremely dense atmosphere, yet its surface is intensely hot and hostile. Titan has a thick atmosphere, but it is so cold that water is as hard as rock. Mars retains a thin atmosphere that cannot sustain stable liquid water across most of its surface. Holding on to gas is only the first condition. Atmospheric composition and pressure determine what kind of world a planet actually becomes. On LHS 1140b, helium exists only in the upper atmosphere and is escaping. Beneath it may lie an atmosphere composed mainly of nitrogen, the dominant gas in Earth's atmosphere. Carbon dioxide could create a greenhouse effect and help retain warmth. Water vapor might take part in clouds, rain, ice, or oceans. It is also possible that the atmosphere is too thin to transport heat efficiently, leaving most of the planet frozen. Nitrogen does not trap heat strongly on its own, but it provides pressure and helps greenhouse gases work more effectively. Carbon dioxide retains heat more efficiently, although too much of it could create a harsh environment. Water vapor is both a powerful greenhouse gas and a substance that readily condenses, creating a complex connection between the atmosphere and the surface. All of these components may exist beneath the helium layer that current instruments cannot yet see clearly. This layered structure also explains how a planet can lose gas while maintaining an atmosphere for a long time. Lightweight atoms in the upper regions continuously escape, while heavier molecules remain trapped below. Over time, the atmosphere changes in composition rather than disappearing completely. It becomes heavier, poorer in hydrogen, and perhaps more stable against the influence of the star. This process is sometimes called atmospheric evolution. Beginning with a primordial layer of gas, a planet undergoes loss, replenishment, and chemical reactions that gradually create a secondary atmosphere. Earth no longer retains its original gaseous envelope either. The atmosphere we have today is the result of volcanoes, oceans, rocks, solar radiation, and biological activity acting over immense periods of time. There is no evidence of biology on LHS 1140b, but geology and radiation alone are enough to drive atmospheric evolution. Hydrogen may have escaped. Helium continues to be lost more slowly. Carbon dioxide may remain in the atmosphere, dissolve into water, or react with rock. Nitrogen may survive for a long time if atmospheric loss is not too severe. For now, we can see only the outermost part of this process. The helium signature is like a small amount of foam drifting away from the surface of deep water. It does not reveal whether the source below is a narrow stream or a vast ocean, but it confirms that material is still moving. Gravity pulls most of the gas back toward the planet. The star provides enough energy for a small portion to escape. Between those forces lies an entire atmosphere in a state of change. LHS 1140b may have survived the most difficult period in the life of its host star. The star is quieter now. The rate of erosion may have declined, and the remaining heavier molecules may be held relatively securely. This creates an opportunity for the lower atmosphere to remain stable over long periods. But the nature of that atmosphere is still a mystery. It may be a thick layer of nitrogen with just enough carbon dioxide to warm the surface, or there may be too little carbon dioxide, leaving the world frozen. An atmosphere rich in carbon dioxide would trap more heat, but high pressure could make the environment very different from Earth. Water vapor may exist in the air, remain locked in ice, or gather within a deep ocean. The struggle between gravity and the star has helped determine what may remain. The lightest gases are the easiest to lose, while heavier molecules have a better chance of surviving. But to discover what the atmosphere below is truly made of, humans must look through the helium layer and search for the more subtle absorption signatures of nitrogen, carbon dioxide, and water vapor. High above, helium is still escaping from LHS 1140b. Beneath it, gravity may be holding a completely different layer of gas, thicker, heavier, and more stable. That deeper atmosphere will determine whether the surface is a frozen sphere, a cold rocky world, or a place with limited regions of liquid water. The next question, then, is no longer whether the planet has retained an atmosphere. The helium signature has shown that at least the upper atmosphere still exists. What must now be discovered is what lies beneath it. After billions of years of radiation, stellar wind, and atmospheric escape, what kind of atmosphere has LHS 1140b managed to preserve? The helium escaping from the upper atmosphere has shown that LHS 1140b is not completely bare. But that signature belongs only to the outermost region of the atmosphere, where the gas has become extremely thin and is beginning to merge with space. The layers that determine the planet's temperature, pressure, and surface conditions lie much deeper. There, starlight must pass through denser gases, where heavier molecules may remain trapped for immense periods of time. It is this lower atmosphere that may reveal whether LHS 1140b is a cold, rocky world, a frozen sphere, or a planet containing a vast amount of water. To investigate these deeper regions, astronomers have used the James Webb Space Telescope. Unlike Weinard, the instrument that helped detect helium in the upper atmosphere, James Webb can observe across several regions of infrared light and search for the absorption signatures of other molecules. Each time LHS 1140b passes in front of its star, some of the starlight travels through the atmosphere. By comparing the light before, during, and after the transit, researchers attempt to identify the extremely subtle changes produced by the deeper layers of gas. One of the first questions was whether the planet is surrounded by a thick hydrogen envelope. Many worlds with sizes between Earth and Neptune possess hydrogen-rich atmospheres. This lightweight gas can make a planet's observed radius appear larger and produce relatively strong spectral features. Such a world is often called a sub-Neptune, not because it is identical to Neptune, but because it has a core or denser interior surrounded by a fairly thick layer of light gas. This was once a reasonable possibility for LHS 1140b. Because the planet is larger than Earth, a hydrogen envelope could have contributed to its observed size. However, data from James Webb did not reveal the strong features that a thick hydrogen atmosphere would normally produce. When atmospheric models were compared with the actual spectrum, many versions of this scenario no longer match the observations. This does not mean that every hydrogen atom has disappeared from the planet. Hydrogen may still exist in small amounts within water vapor, methane, or other compounds. What has become less likely is the idea of a vast hydrogen envelope surrounding the entire planet, like a swollen outer layer that would make LHS 1140b a miniature sub-Neptune. Once this lightweight covering no longer fit the data, the material beneath it became far more interesting. LHS 1140b may therefore resemble a rocky or water-rich world more than a gaseous planet. This is also consistent with the history of atmospheric loss discussed in earlier chapters. Hydrogen is the lightest element and would be the first to escape under the influence of radiation and stellar wind. Over long periods, the upper atmosphere may have become depleted in hydrogen, while helium remained detectable and heavier molecules continued to reside deeper below. There is no contradiction between an upper atmosphere rich in helium and lower layers containing heavier gases. An atmosphere is not a mixture stirred evenly from the surface into space. Even on Earth, density, temperature, and composition change with altitude. Lightweight gases tend to reach higher regions, while heavier molecules are usually concentrated lower down. On LHS 1140b, this separation may be even stronger because the planet has experienced a long history of atmospheric escape. The atmosphere can be imagined as a deep body of water. Lightweight objects rise toward the surface, where they are exposed to winds and currents and may gradually drift away. Heavier objects sink below and remain there for longer. Seeing a few light objects at the surface does not reveal everything contained in the depths. In the same way, helium escaping from the upper atmosphere tells us only about the outermost region, while the atmosphere near the surface may have an entirely different composition. One possibility often discussed is nitrogen. On Earth, nitrogen makes up most of the atmosphere, but does not produce a strong greenhouse effect. Its main role is to provide pressure, allow other gases to function within a stable environment, and help distribute heat through atmospheric motion. A sufficiently thick nitrogen atmosphere around LHS 1140b could transport energy from the side, permanently facing the star toward the dark side, reducing the temperature difference between the two hemispheres. Nitrogen, however, is extremely difficult to detect directly through transit observations. The molecule does not produce strong, distinct infrared features like some other gases. Astronomers often need to search for indirect effects or combine several kinds of data. When certain analyses suggest that the spectrum is more consistent with an atmosphere of heavier molecules, nitrogen remains a candidate worth considering rather than a confirmed component. Carbon dioxide is another important target. This gas absorbs infrared radiation and retains heat. On a planet receiving less energy than Earth, an appropriate amount of carbon dioxide could warm the surface and help prevent some regions from freezing completely. Its influence, however, depends strongly on its abundance, atmospheric pressure, and interactions with clouds, ice, and the surface. Too little carbon dioxide may leave the atmosphere unable to retain enough warmth. Too much could create high pressure and an environment entirely unlike Earth. Venus is the clearest example of why a carbon dioxide-rich atmosphere does not necessarily produce favorable conditions. LHS 1140b receives far less energy, so the outcome would not necessarily resemble Venus. But the comparison still reminds us that greenhouse gases are beneficial only within a certain range. Water vapor is perhaps the most compelling target because it is directly connected to the question of water on the planet. Yet detecting water vapor would not be the same as seeing an ocean. Water vapor could exist above a frozen surface, be released by volcanoes, or appear only in very small quantities. Conversely, a planet with an ocean might still produce a weak water vapor signature if most of its water remains trapped in the lower atmosphere, hidden beneath clouds, or condenses before reaching the regions through which the observed starlight passes. Clouds and haze can also make a spectrum appear almost completely flat. A high cloud layer prevents light from reaching deeper regions, concealing the signatures of molecules closer to the surface. In that case, the absence of clear features does not mean the atmosphere is empty. It may simply mean that the light never reaches the layers containing the information. This is one of the greatest challenges in studying cold exoplanets. James Webb can be imagined as trying to look into a room through frosted glass. A few large objects near the window may still cast shadows, but those farther inside appear only faintly. The frosted glass may represent clouds, haze, or the thickness of the atmosphere itself. Each observation makes the view slightly clearer, but not yet clear enough to identify everything in the room. The current data is therefore consistent with an atmosphere containing molecules heavier than hydrogen, but it does not reveal exactly which gas is dominant. Nitrogen, carbon dioxide, and water vapor all remain on the list of substances requiring further investigation. Other possibilities include a thin atmosphere, high clouds, or a mixture of several components producing a spectrum with almost no prominent features. The first scenario is that LHS 1140b has retained a thick atmosphere. but the environment beneath it is unfavorable for liquid water. The pressure could be extremely high, while the temperature might be lower or higher than expected depending on the atmospheric composition. A dense layer of carbon dioxide could trap a great deal of heat, but it might also make the surface extremely harsh. An atmosphere that survives for a long time does not necessarily create a habitable world. Under this scenario, LHS 1140b might look entirely unfamiliar. Its thick atmosphere could scatter the star's light and create a hazy sky. Clouds might cover much of the planet. Pressure near the surface could be high enough to alter the physical states of water and gases. Although the planet lies within the habitable zone based on its orbital distance, its actual environment could still fall far outside the conditions suitable for life as we know it on Earth. The second scenario is more moderate. The atmosphere may consist mainly of nitrogen, with enough carbon dioxide to retain warmth. On a world that may be tidally locked, winds could carry energy from the day side to the night side. The continuously illuminated region might avoid becoming excessively hot, while the dark hemisphere might remain warm enough to prevent all atmospheric gases from condensing. A stable climate zone could emerge around the transition region or near the point that always faces the star. This is the scenario that most often brings to mind a world with liquid water. Even under these conditions, however, water would not necessarily cover the entire surface. Most of the planet might remain frozen, with only a limited region maintaining higher temperatures. An ocean, if one exists, could lie beneath a layer of ice or remain open only where enough energy reaches the surface. The third scenario is a planet that has retained an atmosphere but remains frozen across most of its surface. LHS 1140b receives less energy than Earth, so the greenhouse effect would need to be strong enough to raise its temperature. A thin atmosphere, or one containing little carbon dioxide, would struggle to melt ice on a global scale. Some locations near the day side might be warmer, while the dark hemisphere and regions far from direct starlight would remain frozen. Ice does not necessarily mean a completely lifeless world. On Earth, life exists beneath sea ice, within sealed lakes, and around regions warmed by geological heat. But there is no evidence of any biological process on LHS 1140b. The image of an icy world only describes a possible climate. It is not a suggestion that life is hiding beneath the surface. A sufficiently thick atmosphere could also create powerful weather systems. The contrast between the day side and night side would drive large-scale winds. Warm air in the illuminated region could rise and move toward the dark hemisphere, while colder air flowed back near the surface. Clouds might gather around the point permanently facing the star, reflecting some of the incoming energy and preventing that region from becoming too warm. Climate models of tidally locked planets often show that clouds can play an important role. A dense cloud layer on the day side may act like a mirror, sending part of the starlight back into space. This could protect the planet from excessive warming. On the night side, clouds and greenhouse gases could retain heat and slow the cooling process. This balance may create a more stable climate than the simple image of one hot hemisphere and one frozen hemisphere would suggest. Everything, however, still depends on the actual amount of gas. An atmosphere that is too thin cannot transport enough heat. The night side could become cold enough for certain gases to condense onto the surface, causing the atmosphere to grow even thinner. A denser atmosphere could prevent this, but pressure and the greenhouse effect would also increase. LHS 1140b may lie anywhere between these states. The presence of helium at high altitude shows only that the planet has not lost all of its gas. James Webb has helped strongly rule out a thick hydrogen envelope, narrowing the possibilities, but the remaining range is still broad. A thin carbon dioxide atmosphere, a dense nitrogen layer, high clouds, or a mixture of several gases could all produce relatively similar data when the number of observations remains limited. This is why exoplanet research requires many transits. The signal from a single observation is usually too weak to distinguish between models that closely resemble one another. As data is combined, faint features may gradually emerge. Carbon dioxide absorbs strongly in certain regions, water vapor leaves signatures in others, and clouds flatten many of those features. Combining observations across multiple wavelengths will gradually eliminate explanations that do not fit. The star must also be observed with great care. Dark and bright regions on its surface can alter the spectrum in ways that resemble a planetary atmosphere. Red dwarfs do not emit perfectly stable light, especially in infrared and ultraviolet wavelengths. To determine whether an absorption signature comes from LHS 1140b, researchers must understand the host star almost as thoroughly as they understand the planet. This makes the search slower, but also more reliable. Rather than choosing the most exciting explanation, science tests each possibility. A signal resembling water vapor must be compared with the influence of the host star. A possible carbon dioxide signature must appear repeatedly across the appropriate regions of light. A nitrogen atmosphere would need support from pressure and other indirect effects, rather than relying on a single spectral line. At the current stage, the clearest conclusion is that LHS 1140b no longer resembles a typical sub-Neptune. The thick hydrogen envelope, once considered a leading possibility, does not agree with the newer data. This has increased interest in models involving a solid surface, ice, or water surrounded by an atmosphere of heavier molecules. But a rocky planet and a water-rich world are not entirely separate possibilities. LHS 1140b may have a rocky interior covered by a deep layer of water and then an atmosphere above it. It could also be a rocky planet with a more moderate amount of water concentrated beneath ice. Its mass and size allow for many different proportions of iron, rock, water, and gas. The atmosphere acts as a connecting layer between the interior and space. Volcanoes may release carbon dioxide and water vapor. Oceans absorb gases and later release them again. Ice stores water and changes how much light the planet reflects. Rocks react with carbon dioxide, helping regulate the climate over long periods. To understand the atmosphere, we must ultimately understand the material beneath it. On Earth, the atmosphere cannot be separated from the oceans and crust. Carbon moves between the air, water, rocks, and living organisms. Water vapor rises, forms clouds, and falls again. Nitrogen is transformed through many chemical processes. LHS 1140b may not possess the same cycles, but the general principle remains true. An atmosphere reflects both the history and the structure of its planet. A rocky world may release gases differently from a planet with a deep ocean. Water can absorb carbon dioxide, while high-pressure ice and layers of rock may prevent exchange with the interior. The atmosphere above may therefore reveal whether the planet remains geologically active or has become isolated between layers of material. James Webb has so far opened only a narrow window. The data suggests that a vast envelope of lightweight gas is unlikely, but it does not clearly reveal what lies in the room beyond the curtain. Nitrogen remains possible. Carbon dioxide and water vapor are still being sought. Clouds, haze, and the limitations of the instruments continue to conceal many details. Even so, eliminating one important scenario has changed the way we view LHS 1140b. The planet can no longer be easily described as a sub-Neptune with a surface buried beneath a hydrogen envelope. The possibility of a world with an accessible surface or an ocean has become more significant. This is not evidence of liquid water, but it is a step toward narrowing the distance between a small gaseous planet and a world whose structure more closely resembles the rocky planets. Above, helium continues to escape. Beneath it, a heavier atmosphere may remain calmer and more tightly bound by gravity. Deeper still lies the material that determines the entire story: rock, ice, water, or some combination of them. Each layer influences the others, creating a planet that cannot be understood through a single absorption signature. To discover what the atmosphere contains, scientists must continue looking more deeply into the light. But to explain which gases may exist there, they must also answer another question. What kind of material is LHS 1140b truly made of? This planet may not be an ordinary rocky super-Earth. Its mass and size allow for a more compelling possibility that beneath the heavier atmosphere it has managed to retain may lie a world containing far more water than Earth. Beneath the atmosphere of LHS 1140b lies a part of the world that has never appeared in any image. Telescopes have not seen its surface, distinguished ice from rock, or revealed the shoreline of an ocean. Yet the planet's mass and size have left an intriguing clue. It is not as dense as a sphere made only of iron and rock with a structure similar to Earth's. Among the materials that could account for what is missing, water provides an explanation consistent with many models. Some calculations allow water to make up roughly 1/10 to nearly 1/5 of the planet's total mass. That may not sound like an enormous amount until it is compared with Earth. Oceans cover most of our planet's surface, yet all the water on Earth represents only a tiny fraction of its total mass. The interior remains composed mainly of rock and metal. On LHS 1140b, the amount of water suggested by the models exists on an entirely different scale, enough to create an ocean layer deeper than anything familiar to us, or an immense shell of ice surrounding a rocky interior. The available data does not prove that water is truly present in such quantities. Mass and radius only allow researchers to test different internal structures and determine which ones fit best. A planet made entirely of rock and iron would have a higher density. A layer of lighter material, such as water, ice, or atmosphere, would lower the average density. After a thick hydrogen atmosphere became less consistent with the observations, water-rich models began receiving greater attention. There is therefore no single picture of the interior of LHS 1140b. A metallic core may lie at the center, surrounded by a thick layer of hot rock. Above the rock could be water, with its physical state changing according to depth. Near the surface, it may be frozen or liquid. Farther down, the weight of the entire ocean could create enough pressure to force water molecules into unusual solid structures. This kind of ice does not require the extremely low temperatures that form ice on the surface of a lake. It is created by pressure. Water above it may remain liquid while the deeper layers become solid. A shell of high-pressure ice would then lie between the ocean and the rocky interior, separating two environments that remain in direct contact on Earth. This separation may be more important than it first appears. On the floor of Earth's oceans, water enters cracks in the crust, comes into contact with hot rock, dissolves minerals, and returns through hydrothermal vents. These reactions carry many elements into seawater. On land, rain breaks down rock and carries material through rivers into the ocean. The atmosphere, water, and crust continuously exchange substances with one another. An ocean resting above a thick layer of ice would have far less access to the rock below. Minerals would struggle to rise, while substances dissolved in the water would have difficulty returning to the planet's interior. The chemical system would become more isolated. A vast amount of water, therefore, would not necessarily create an environment richer than Earth's. Sometimes, abundance itself can sever important connections. An ocean world might also have no continents at all. There would be no shorelines, no dry land, and no shallow regions where light, water, and minerals meet. On Earth, many coastal environments undergo constant transitions between wet and dry, warm and cold, fresh water and salt water. These regions are often chemically active. If LHS 1140b were entirely covered by water, it would operate according to a very different order. That immense body of water would also exist beneath the light of a red dwarf. The star is smaller and cooler than the Sun, and emits most of its energy in red and infrared wavelengths. Ice strongly reflects visible light but absorbs more efficiently at certain infrared wavelengths. A frozen surface around a red dwarf may therefore respond to starlight differently from the way ice on Earth responds to sunlight. Regions receiving direct illumination could absorb more heat than a simple comparison might suggest. The planet's close orbit introduces another possibility. LHS 1140b may be tidally locked. This does not mean the planet has stopped rotating. It still turns on its axis, but it completes one rotation in exactly the same amount of time it takes to complete an orbit. As a result, nearly the same side always faces the star. The Moon is in a similar state with Earth, which is why we always see nearly the same side of it. On LHS 1140b, the host star would appear almost motionless in the dayside sky. The opposite hemisphere would receive no direct starlight. Between the two halves would be a transitional band encircling the planet, where the red star remained low near the horizon like a sunset that never ends. Tidal locking remains a result of orbital modeling. No direct observation has confirmed that the surface of LHS 1140b always keeps the same side facing its star. Its close orbit, however, makes this scenario plausible enough to appear in many climate studies. One bright hemisphere and one dark hemisphere often suggest an extreme image, a scorched dayside and a frozen nightside. In reality, the outcome would also depend on the atmosphere. Moving air could carry heat away from the illuminated region. A deep ocean could transport energy through currents as well. Warmth would not necessarily remain trapped at a single point, just as cold would not necessarily dominate the entire dark side. At the region facing directly toward the star, light would shine continuously. There would be no afternoon allowing the surface to cool and no night during which heat could escape after sunset. Water there would receive more energy than in other regions. Farther from this central point, the star would appear lower in the sky, the amount of warmth would decrease, and the ice would gradually thicken. The night side would become an immense cold reservoir where water might remain locked in ice for extremely long periods. From this pattern emerges a well-known scenario, the eyeball world. The planet would be almost entirely covered in ice, but at the center of the dayside, a darker region of liquid water, circular or nearly circular, would remain permanently facing the star. Surrounding it would be rings of ice extending toward the night side. Seen from a distance, the open water would resemble a pupil set within a white sphere. The name is vivid, but it does not come from direct observation. No telescope has ever seen an eye of water on LHS 1140b. It is simply one possible state allowed by climate models when the amount of incoming heat, atmospheric thickness, and efficiency of energy transport fall within the right range. That region of liquid water would not necessarily have a clearly defined shoreline. Temperatures would gradually decrease outward from the warmer center. Floating ice could break apart, drift into the open water, and melt, while other bands of ice were carried by currents toward colder regions. The boundary would shift continuously with winds, clouds, and ocean circulation, even if its overall position remained centered on the dayside. A sufficiently thick atmosphere would expand the open water region. Winds would carry heat across great distances, reducing the contrast between the two hemispheres. The night side would no longer become cold enough for every atmospheric component to condense onto the surface. The transition zone would grow warmer, and the ice would retreat farther from the point receiving the most direct light. A very thin atmosphere would produce the opposite result. Heat would struggle to move away from the dayside. The night side would remain deeply frozen, and the liquid water region would shrink or disappear. Clouds would play an especially important role near the point that always faces the star. Water would evaporate, warm air would rise, and condensation would occur at higher altitudes. A dense cloud system could form in a nearly permanent location, reflecting some of the incoming starlight back into space. This would prevent the continuously illuminated region from necessarily warming out of control. Clouds would cool the surface by blocking light while also trapping infrared heat below. The balance between these two effects would help determine the state of the water. After rising, the air would spread outward, gradually cool, and descend in other regions. Water vapor would be carried toward the night side, where it would freeze onto the surface. Over time, water might migrate away from the warm region and accumulate across the dark hemisphere. Ocean currents or drifting ice would need to return some of that water, or the dayside could gradually lose its surface supply. Such a cycle would be very different from Earth's water cycle. Here, the sun crosses the sky, continents divide the flow of air, and seasons change with orbital position. On LHS 1140b, the light source would remain almost fixed. Regions of rain, cloud, or ice could stay anchored around long-lasting locations. The climate would be organized by distance from the point facing the star, rather than by day and night, as it is on our planet. A deep ocean would make the entire system respond more slowly. Water stores heat efficiently and takes a long time to warm or cool. Currents beneath the surface could transport energy through regions receiving no direct light. With no continents blocking their paths, ocean currents could move freely around the planet, although the slow rotation and stronger gravity would create circulation patterns very different from those in Earth's oceans. Such an ocean would not necessarily appear blue. A red dwarf provides a different kind of light, the atmosphere may be thick, and clouds or haze could alter the color of the sky. Water beneath deep red illumination might appear almost black. Ice around the edges could absorb more infrared radiation and look gray rather than brilliant white. The star would remain fixed above the water, appearing larger in the sky but gentler than the Sunday. These images help describe a possibility, not a confirmed landscape. LHS 1140b could also be completely frozen. It receives less energy than Earth, while the composition of the atmosphere beneath the helium layer remains unknown. Without a sufficiently strong greenhouse effect, even the center of the dayside might be unable to sustain liquid water for long. In that case, the entire surface would become one continuous shell of ice. The dayside would be warmer, but not warm enough to melt. The night side would remain bitterly cold and hold vast amounts of ice. Water could still make up a significant portion of the planet, but it would not appear as surface seas or lakes. Heat from the planet's interior might still preserve an ocean beneath the ice. LHS 1140b is larger than Earth and may cool more slowly, while radioactive decay within its rocks would continue releasing energy. Tidal friction might also contribute, depending on the planet's orbital state. Beneath a thick frozen crust, liquid water could survive in darkness, completely isolated from the atmosphere. Such a world would bring Europa or Enceladus to mind, but on a much larger scale. A cold surface does not rule out a hidden ocean. Even so, there is no evidence that LHS 1140b truly has this structure. Its mass and radius cannot clearly distinguish whether the water lies on the surface, beneath ice, or within deeper layers. The atmosphere cannot yet provide a definite answer either. Even a future detection of water vapor would not automatically prove the existence of an open ocean. Ice exposed to starlight could release small amounts of vapor. Geological activity might carry water upward from the interior. Clouds and temperature would determine how much vapor remained in the part of the atmosphere visible to telescopes. In the opposite direction, a dry-looking spectrum would not rule out an ocean. Low temperatures could keep water vapor close to the surface. High clouds might conceal the deeper layers. An ocean locked beneath ice would exchange almost nothing directly with the atmosphere. A planet containing an enormous amount of water could still produce only a weak water vapor signature. The presence of water alone, therefore, does not bring life into the story. Liquid water is an important solvent for biology on Earth, but a long-lasting habitable environment also requires energy sources, essential elements, and cycles that reuse material. An ocean isolated from rock may struggle to obtain minerals. An extremely deep ocean would create immense pressures. An atmosphere that is too thick or too thin could move the environment far beyond familiar conditions. Earth is not favorable simply because it has seas. The ocean floor exchanges material with the mantle. Continents undergo weathering. Carbon moves through the air, water, and rock. Volcanoes return gases to the atmosphere. These processes help regulate the planet's temperature over immense spans of time. A completely water-covered world without exposed land may not be able to maintain the same kind of system. A layer of high-pressure ice would create another barrier between the water and the interior. Heat could still pass through, but material exchange would be more difficult. Some chemical reactions requiring direct contact with minerals would be restricted. The ocean might be vast enough to cover the entire planet, while still lacking many of the ingredients needed for complex chemistry. Other pathways, however, cannot yet be ruled out. Cracks within the high-pressure ice, convective currents, or strong geological activity might transport material through the layers. Some minerals may have dissolved into the water during the planet's formation. Impacts could also add new components. We do not yet understand enough to conclude that a deep ocean would necessarily be poor in nutrients. The origin of the water itself is also mysterious. LHS 1140b may have formed in a colder region of the system, where ice was abundant, before migrating into its current orbit. It may also have acquired water from smaller bodies that struck it early in its history. Some water could have remained trapped within minerals, and later been released as the interior heated. Each history would create a different kind of ocean, water mixed with ammonia, salts, carbon dioxide, or other volatile substances would have its own freezing point, density, and chemistry. A salty ocean could remain liquid at temperatures below the freezing point of pure water. Ammonia would also lower the freezing point. The familiar image of a blue sea may therefore be entirely inappropriate. The water-rich possibility remains compelling because it provides a reasonable explanation for the density of LHS 1140b. The planet is too large to be described simply as a second Earth, yet it does not resemble a typical sub-Neptune now that a thick hydrogen envelope appears less consistent with the data. Between these two groups lies a kind of world not found in our solar system, a rocky or icy planet containing an immense amount of water and surrounded by an atmosphere of heavier molecules. For now, science holds only a few pieces of the puzzle. The planet's mass and size allow for a water-rich structure. Atmospheric data weakens the thick hydrogen scenario. Helium in the upper atmosphere shows that the planet still retains gas. Its orbit opens the possibility of tidal locking. From these separate pieces, the eyeball world model has been constructed. But a model is not a photograph. It answers only one question. What might the surface look like if the planet contains a great deal of water, has a moderately thick atmosphere, and keeps one side permanently facing the star? Under those conditions, a region of liquid water could survive within the ice. Change any one of those conditions, and the entire picture changes. A thinner atmosphere would allow the water to freeze. A thicker atmosphere would expand the warm region. Clouds would reflect starlight, ocean currents would transport heat, and atmospheric composition would regulate the greenhouse effect. Future observations will gradually narrow these possibilities. Carbon dioxide could reveal how strongly the atmosphere retains heat. Water vapor would provide further clues about a possible water cycle. Atmospheric pressure in clouds could help predict the contrast between the day side and night side. Even then, confirming an ocean would require several kinds of evidence rather than a single spectral signature. LHS 1140b may be a deep water world, an ice-covered sphere with a hidden ocean, or an eyeball planet with open water on its day side. It may also possess a structure that does not appear in any simple model. We are trying to understand this world only through the shadow it casts and the fragments of light held back by its atmosphere. An ocean is compelling because life on Earth began in water, but the similarity may end there. Any sea on LHS 1140b could be hundreds of times deeper, darker, subject to stronger gravity, and located beneath a permanently red sky. At the bottom may be not rock, but a dense layer of ice separating the ocean from the planet's interior. The presence of water does not guarantee favorable conditions, nor is the existence of an atmosphere enough. A planet with both could still be cold, deprived of minerals, exposed to extreme pressures, or unable to sustain the chemical cycles that complex environments require. The question of LHS 1140b should therefore not end with whether an ocean exists there. What matters more is where that ocean lies, what it touches, how it receives energy, and how long it has remained stable. Only when those pieces are understood will water truly become meaningful to the question of habitability. The image of a single eye of water within a frozen sphere remains before us as a beautiful but unconfirmed possibility. It helps reveal the diversity of worlds that may exist beyond our solar system, but it does not allow us to call LHS 1140b a place where life exists, because even a planet with an atmosphere, ice, and a vast ocean may remain completely silent. The image of an ocean resting within a frozen sphere can make LHS 1140b seem more familiar than it truly is. As soon as water, clouds, and an atmosphere enter the picture, the human imagination begins to envision blue skies, distant shorelines, or some form of life hidden beneath the surface. But the data does not take us that far. So far, no observation has revealed living organisms, biologically produced oxygen, vegetation, or the confirmed existence of an ocean on the planet. The helium signature in the upper atmosphere is not a sign of life. Helium is a common element throughout the universe, formed during the earliest stages of cosmic history, and still found in stars, gas planets, and the interiors of rocky worlds. Its presence around LHS 1140b tells us only that the planet has retained an atmosphere and that part of this gas is escaping into space. It reveals nothing about whether biology exists on the surface. A biologically lifeless world can still possess an atmosphere. Venus is surrounded by a dense layer of gas, planet-wide clouds, and powerful weather systems, yet its surface is hot enough to melt lead. Titan has a nitrogen-rich atmosphere, clouds, and lakes of liquid, but those liquids consist mainly of methane and ethane at extremely low temperatures. Mars still has air and weather cycles, although its atmosphere is too thin to support stable liquid water across most of the surface. An atmosphere is therefore a physical condition, not a biological certificate. It transports heat, creates pressure, protects the surface from some radiation, and participates in chemical reactions. These functions may help life survive, but they do not create life by themselves. Many other factors are required, including stable liquid water, sources of energy, suitable chemical elements, and an environment that remains favorable for long enough. The phrase, habitable zone, is also often interpreted more broadly than its actual meaning. It does not describe a region filled with planets that certainly have oceans, plants, or living organisms. It refers only to the range of distances around a star where the amount of received energy could allow liquid water to exist on the surface under certain suitable atmospheric conditions. The final part of that definition is especially important. Liquid water depends not only on distance from the star, but also on atmospheric pressure and composition. A planet receiving a moderate amount of light may still freeze if its atmosphere is too thin. If its gases trap heat too efficiently, the surface may instead become intensely hot. Clouds reflect light, ice changes how much energy is absorbed, and oceans and winds determine how that energy is distributed. The habitable zone merely places a planet within an orbital range worth investigating. It opens a door from a thermal perspective, but it does not reveal what lies behind that door. Earth and Venus provide the clearest reminder. The two planets are relatively similar in size, formed within the same solar system, and both possess atmospheres. Yet their final conditions are completely different. Earth maintains oceans on its surface, while Venus is covered by a thick carbon dioxide atmosphere, immense pressure, and extreme temperatures. Their distances from the sun helped create this difference. But distance was not the only factor. Water, clouds, geological activity, atmospheric loss, and their developmental histories pushed the two planets along separate paths. A small difference in the beginning, given billions of years, was enough to create two almost opposite worlds. LHS 1140b also has its own history, much of which remains unknown. The planet lies within an orbital region where liquid water cannot be entirely ruled out. Its large mass helps it retain gas. Its star is now relatively quiet. These advantages make it an appealing target for observation, but they are not enough to describe the surface. To evaluate the planet's true environment, atmospheric pressure is one of the first questions that must be answered. An atmosphere that is too thin would struggle to transport heat from the day side to the night side. The dark hemisphere could become a vast cold trap where some atmospheric gases condense onto the surface. A thick atmosphere would distribute heat more effectively, but high pressure could also create conditions unfamiliar to life on Earth. Chemical composition determines how strongly the atmosphere retains heat. Nitrogen provides pressure but does not absorb heat efficiently. Carbon dioxide can warm the planet, although excessive amounts would profoundly alter the surface temperature and chemistry. Water vapor is also a powerful greenhouse gas and participates in clouds, snow, and climate cycles. Simply knowing the names of the gases would still not be enough. Their proportions are what shape the climate. A small amount of carbon dioxide within a thick nitrogen atmosphere would create a completely different environment from one composed almost entirely of carbon dioxide. A weak water vapor signature at high altitude could exist above a cold ocean, or it might come only from evaporating ice. The same spectral feature can sometimes support several different explanations. The planet's average temperature can also conceal extreme regional conditions. On a tidally locked world, the day side and night side experience two very different energy regimes. The global average may sound suitable even while half the surface remains too cold and the other half lies beneath dense clouds. Life, if it ever appeared, would not live within an average number. It would exist in specific environments. Ultraviolet radiation and X-rays from the host star create another layer of difficulty. These forms of radiation heat the upper atmosphere, break molecules apart, and alter its chemistry. They may also reach the surface directly if the atmosphere is not thick enough to absorb them. A star that is quiet today may not have been quiet in its youth. The present atmosphere is what remains after that entire history. The surface beneath the atmosphere must also be understood. Dry rock, ice, deep oceans, and continents create very different chemical cycles. Water in direct contact with rock can receive minerals from the planet's interior. An ocean resting above high-pressure ice would be separated from those deeper mineral sources. Habitability depends not only on whether water is present, but also on how that water interacts with the rest of the world. Geological activity plays a similar role. Volcanoes replenish the atmosphere by carrying carbon dioxide, water vapor, and many other compounds upward from the planet's interior. Rocks react with the air and trap some of its carbon. If these cycles continue for long enough, they may help regulate the climate. A planet that has cooled completely would lack this source of replenishment, causing its atmosphere to evolve along a different path. On Earth, life also participates in these cycles, but before searching for biology, researchers must first understand the geological foundation. Methane in an atmosphere could come from microorganisms, but it can also be produced when water reacts with hot rock. Oxygen may be released through photosynthesis, yet stellar radiation can also split water molecules and allow oxygen to accumulate under certain conditions. Carbon dioxide is consumed by living organisms, but it is also a natural product of volcanic activity. For this reason, no single gas is powerful enough to prove that life exists. Oxygen is often considered an intriguing signal because most of the oxygen in Earth's atmosphere is maintained by photosynthetic organisms. However, a planet that has lost large amounts of water could accumulate oxygen after hydrogen escapes into space. Ultraviolet light can also break apart carbon dioxide and release oxygen in certain environments. Without understanding the star and the history of the atmosphere, an observer could easily mistake an abiotic product for a sign of biology. Methane carries a similar ambiguity. On Earth, living organisms produce a significant amount of methane, yet a planet's interior, reactions between water and rock, and volcanic activity can also create methane without any biology. A small methane signature on an exoplanet would be an interesting clue, but it would not be an answer. Researchers pay greater attention to chemical disequilibrium. An atmosphere containing gases that readily react with one another cannot remain in that state for long unless something continues to replenish them. Oxygen and methane are a familiar example. When both exist in significant amounts, they gradually react and reduce each other's concentrations. If they remain present together, some process must be continually producing more of them. On Earth, biology is an important source that maintains this disequilibrium. But applying the same explanation to another planet still requires caution. Volcanoes, photochemistry, and interactions between water and rock can sometimes produce intriguing combinations of gases. Every potential biosignature must be considered within the full context of the planet. A spectrum is therefore more like a chemical record than a declaration. One absorption line may identify a gas. Several different lines can reveal the proportions among atmospheric components. Information about the star shows which reactions its radiation may be driving. The planet's mass, temperature, and surface structure help researchers evaluate possible geological sources. Only after these pieces are assembled does a biological hypothesis begin to carry meaning. Even a combination of gases that is extremely difficult to explain through non-biological processes would not immediately end the debate. Other research teams would need to repeat the observation. Different instruments would have to detect the same signatures. Climate, photochemical, and geological models would be tested independently. Interference from the star would need to be ruled out. The closer science comes to a major claim, the stricter the standard of evidence becomes. This caution does not make the journey less compelling. On the contrary, it protects science from turning a faint signal into a story too soon. These exoplanets are far too distant for probes to reach in the foreseeable future. Everything we know comes from a handful of photons, a few transits, and tiny changes in light. Every conclusion must be strong enough to withstand those limitations. LHS 1140b shows how science advances slowly but clearly. Before its discovery was announced in 2017, it was simply an unnoticed variation in the light among countless stars. The first transits revealed that a planet was passing in front of the star and completing its orbit at a regular rhythm. The depth of the dimming revealed its size. Later, the wobble of the star helped determine the planet's mass. The portrait of an extremely dense rocky world began to change as its density was measured more precisely. The possibility of a water-rich planet entered the story, not through an image of an ocean, but through the combination of its size and mass. James Webb narrowed the possibilities further. A thick hydrogen envelope, characteristic of a sub-Neptune, did not fit the data. Atmospheres containing heavier molecules became more worthy of consideration. Nitrogen, carbon dioxide, and water vapor have not yet been firmly confirmed. But the range of possibilities is narrower than it was before. The helium signature in the upper atmosphere added another piece. The atmosphere no longer exists only within structural models. Part of it truly leaves an absorption signature when the planet transits. Helium also shows that material is interacting with the star and gradually escaping into space. No single step answers the entire question, and none stands alone. Size combined with mass gives density. Density introduces the water-rich scenario. Spectroscopy weakens the thick hydrogen model. Helium confirms the upper atmosphere. Each measurement removes some possibilities, while preserving those that better fit the evidence. It would therefore be inaccurate to say that humans know nothing about LHS 1140b. We know that the planet is larger than Earth, has strong gravity, orbits a relatively quiet red dwarf, and receives an amount of energy that does not entirely rule out liquid water. We know that a thick hydrogen envelope is difficult to reconcile with the data. We also know that its upper atmosphere contains enough helium to produce a signal that changes over time. Yet the unknown territory remains vast. Atmospheric pressure has not been determined. The composition of the lower atmosphere remains unclear. No ocean has been seen. Tidal locking has not been directly confirmed. No biosignature has been detected. But the boundary between what is known and what remains unknown has grown sharper. This is how science truly advances. It does not always find an answer after a single observation. More often, it transforms one vague question into many smaller questions that can be tested. The planet began as nothing more than a dark point crossing its star. Now we can ask whether its atmosphere is thick or thin, rich in hydrogen or heavier molecules, whether its surface is rocky or water-rich, and whether its upper atmosphere is stable or escaping. Life lies at the end of a long chain of questions, not at the beginning. Before searching for organisms, we must know whether the environment is stable. Before speaking of a stable environment, we must understand the atmosphere, temperature, and surface. Before interpreting the spectrum, the host star must be studied carefully enough to eliminate false signals. Each layer of understanding supports the next. Future observations may search for carbon dioxide, water vapor, or indirect signatures of nitrogen. Measuring heat differences between the day side and night side could reveal how efficiently the atmosphere transports energy. Monitoring ultraviolet radiation and X-rays would help explain the energy driving the upper atmosphere. Additional transits will test whether helium appears according to a cycle, follows stellar activity, or changes with the evolving shape of the outflow. The picture is gradually shifting from a static image into a history of motion. LHS 1140b does not merely have a size and mass. It receives energy, loses gas, retains heavier molecules, and may experience an uneven climate between its two hemispheres. Understanding these processes is more important than rushing to label the planet habitable. The question of whether a planet has life is too large for any single measurement to answer. More practical questions lie closer to what humans can currently investigate. Which gases are present, how abundant they are, how the climate responds, and what processes maintain that state. As these smaller questions are gradually answered, the possibility of biology can be evaluated on firmer ground. Any intriguing future signal would not appear within an empty space of understanding, but within an existing picture of the star, atmosphere, ocean, and planetary interior. LHS 1140b has not revealed life, nor has it become a second Earth. Its value lies elsewhere. It is one of the nearby worlds where humans may gradually test how a large rocky planet retains gas, loses gas, and preserves water within the environment of a red dwarf. The final question, then, is no longer simply whether organisms exist there. For now, what matters more is where humans should look, which components must be measured precisely, and which future transits may allow the picture to grow clearer. An answer about life, if life exists there, will not come from a single sign. It will emerge only after many independent pieces of evidence point toward a world that non-biological processes can no longer fully explain. LHS 1140b will pass in front of its host star many more times. During each transit, starlight will once again pass through the edge of the atmosphere for a few brief hours before the planet continues along its orbit. From Earth, almost nothing about the appearance of the star will seem to change. It will remain only a tiny point of light. But for spectrographs, every transit is another opportunity to determine whether the helium signature returns. A single detection opens a hypothesis. Repeated detections begin to reveal a pattern. If the absorption signature reappears at the correct wavelength, moves with the planet, and retains similar characteristics, the conclusion about the helium layer will become stronger. Variations between observations will no longer appear merely as anomalies. They will become data, showing how the upper atmosphere responds to the environment around the star. The strength of the signal, the width of the absorption line, and the moment when it begins to appear all contain information. Helium becoming visible before the body of the planet enters the stellar disk would suggest a region of gas extending ahead of it. A signal that remains after the planet has completed its transit would be more consistent with a tail trailing behind. Changes in these shapes can help reconstruct the structure of the outflow, even though no telescope can photograph it as an ordinary cloud. After many transits, researchers may also be able to estimate how much material is leaving the planet. This is not a simple measurement. The helium signature represents only one part of the escaping gas, while the number of atoms in the observable state depends on temperature and radiation from the star. To convert a small absorption line into an atmospheric loss rate, models must account for gravity, upper atmospheric density, gas composition, and the amount of energy entering the system. The result will therefore not be a single absolute number that never changes. More likely, it will be a range of values that gradually narrows as more data is collected. A long sequence of observations can reveal whether the escape rate is steady, fluctuating, or changing with the activity of the host star. From there, the history of the atmosphere may slowly emerge. How much gas has been lost, what portion has remained, and whether the present process is still strong enough to alter the planet in the future. Long-term monitoring will also address another fundamental problem: distinguishing real variation from noise. Every night of observation takes place under different conditions. Humidity in Earth's atmosphere changes, instruments introduce small errors, and new active regions appear on the surface of the star. A weak absorption signature may stand out in one dataset, but sink into the noise in another. The longer the observing record becomes, the easier it is to identify random effects. Ground-based observatories will play a major role in this work. Weinard and other high-resolution infrared spectrographs can monitor helium across many transits without requiring a large space telescope to devote time to every event. Ground-based telescopes are also more flexible in returning to the target over several observing seasons, allowing scientists to build a record of changes in the upper atmosphere. Each measurement will resemble a page in an atmospheric diary. The first page shows helium clearly. The next is almost blank. Only the pages that follow can reveal whether that silence was an exception, part of a cycle, or a sign that the outflow changes unpredictably. Once the diary becomes long enough, the upper atmosphere will begin to appear as a system with a history rather than a handful of isolated moments. While ground-based telescopes monitor helium, James Webb has a different task. The infrared wavelengths it observes can be used to search for heavier molecules deeper in the atmosphere. Carbon dioxide is an important target because it strongly influences the planet's ability to retain heat. Water vapor is directly connected to a possible water cycle, although its presence alone would not prove that an ocean exists. Other absorption signatures may help determine whether the atmosphere consists mainly of nitrogen, carbon dioxide, or a more complex mixture. The difficulty lies in the size of the signal. LHS 1140b is much colder than many exoplanets commonly studied through transmission spectroscopy. A cold atmosphere has a smaller vertical extent, so the gases along the planet's edge block very little additional starlight. High clouds or haze can flatten many spectral features even further. A single transit is often not enough. Multiple datasets must be combined before faint signatures can gradually rise above the noise. James Webb also cannot measure nitrogen directly as easily as it can carbon dioxide. Nitrogen leaves few strong absorption features in the wavelengths commonly used for these studies. Its presence may need to be inferred indirectly through atmospheric pressure, collisions between molecules, or its influence on the overall spectrum. For this reason, determining whether the atmosphere is truly rich in nitrogen will require several techniques working together rather than a single absorption line. Ultraviolet radiation from the star is another essential piece of the puzzle. Helium in the upper atmosphere leaves a detectable signature only when it receives the right kind of energy. Ultraviolet light and X-rays heat the gas, ionize atoms, and control how much helium occupies the special state that instruments can detect. Without knowing precisely how much high-energy radiation the star emits, every estimate of the atmospheric escape rate will carry substantial uncertainty. Observations with Hubble, X-ray telescopes, and future ultraviolet instruments will help measure this radiation environment. The data must be collected close to the time of each planetary transit because red dwarfs do not maintain the same level of activity every day. A flare occurring before an observation may cause the upper atmosphere to expand. A prolonged quiet period may weaken the signal. Comparing the star's high-energy emissions with the helium signature will reveal whether the two truly change together. The magnetic field and stellar wind will remain more difficult to observe. Streams of charged particles do not appear directly in a spectrum the way gas molecules do. Researchers must infer their influence from the shape of the helium outflow, the activity of the star, and plasma models. A gas tail displaced from the orbital path, an absorption region appearing early, or irregular changes in the signal may all carry traces of the stellar wind. As more data is gathered, the geometry of the upper atmosphere will become less uncertain. Instead of knowing only that helium exists, scientists will begin asking where it is distributed, which direction the outflow extends, and how broad the escaping region may be. A nearly symmetrical layer of gas surrounding the planet tells a different story from a long tail swept away by the stellar wind. Both involve atmospheric loss, but the mechanisms and rates may be very different. The source of helium from below has not yet been determined either. Some may be left over from the planet's primordial atmosphere. Another portion may be produced within its rocks and gradually released upward. Geological activity, radioactive decay, and the transport of gas through the crust may all contribute. To determine which source is most important, researchers must compare the rate of atmospheric loss with the amount of helium the planet's interior may be able to replenish. A strong supply from below could allow the helium outflow to persist even as atoms continuously escape. A weaker source would mean that the present signal is only the fading remnant of a reservoir being depleted. These two scenarios imply very different atmospheric histories, but no existing measurement can yet distinguish between them with confidence. Beneath the helium layer lies the question of the atmosphere's total thickness. A thin atmosphere would create little pressure, transport heat poorly, and allow the night side to become deeply cold. A thicker atmosphere would reduce the temperature contrast between the two hemispheres. A greater abundance of gas molecules would also increase infrared absorption, changing where ice could melt and where liquid water might survive. The temperature difference between the day side and night side may one day be studied by tracking the light emitted as the planet moves around its star. A world with almost no atmosphere would heat up strongly on the illuminated side and cool rapidly in darkness. A thick atmosphere or deep ocean would carry heat farther, making those variations smaller. This measurement is extremely difficult for a cold, distant planet, but future telescopes may achieve the sensitivity required. The surface of LHS 140b remains hidden behind a veil even more impenetrable than its atmosphere. Oceans, ice, and rock reflect light differently, but the planet is too small to be seen separately beside its star. No shoreline has appeared in the data. No map of bright and dark regions reveals where water might lie. Models of the planet's interior must still rely mainly on its mass, radius, and atmospheric composition. More precise measurements of its mass will continue to narrow the amount of water the planet could contain. Its radius must also be monitored carefully, because active regions on the star can slightly alter the apparent depth of a transit. Even a small error in either measurement can significantly shift the estimated proportion of water. The better we understand the star, the more reliable the portrait of the planet's interior becomes. Another major question points toward the past. LHS 1140 is relatively quiet today, but its youth may have been very different. Red dwarfs often take a long time to settle down, emitting much stronger high-energy radiation during their early stages than they do today. The planet would have endured this harsh environment precisely while its atmosphere and surface were still forming. The star's history of activity determines how much hydrogen was lost, how much water was broken apart, and how extensively the atmosphere may have been rebuilt afterward. Astronomers will study the star's rotation, magnetic activity, and similar stars to reconstruct the youth of LHS 1140. No one can directly observe the star as it existed billions of years ago, but traces of its age remain in its present motion and activity. By combining the star's radiation history with the rate of atmospheric escape, models can test how the planet survived its most violent era. Strong gravity may have been the dominant factor. An initially massive atmosphere could also have provided a large enough reservoir. Volcanoes and a hot interior may have replenished gases after the most intense period of erosion ended. We do not yet know which path LHS 1140b followed, but the atmosphere that remains today proves that at least one path succeeded. Its neighboring planet, LHS 1140c, will continue to serve as a useful comparison. Both worlds orbit the same star, but they differ in size and in the amount of radiation they receive. The absence of a clear helium signature around Planet C could reflect an atmosphere that has been stripped away, a different composition, or simply a signal below the detection limit. Further observations will reveal whether the contrast between the two worlds is truly connected to the cosmic shoreline. Beyond this system, thousands of other planets are waiting to be examined. Time on James Webb is precious. While not every world within a habitable zone still possesses an atmosphere, devoting many transits to searching for water vapor on a planet that has already lost all its gas would be unlikely to produce useful results. Helium may offer a more efficient way to select promising targets. Ground-based observatories can first examine the upper atmosphere. An extended helium signature shows that material is still present and interacting with the star. Such a planet may deserve additional observing time with more powerful instruments. When no signal is found, the conclusion must still remain cautious, because helium may not occupy the observable energy state. Even so, the target can be evaluated alongside other evidence before entering expensive observing programs. Helium does not search directly for life. It cannot distinguish a lifeless ocean from one filled with organisms, nor does it reveal carbon dioxide, nitrogen, or pressure near the surface. The value of helium lies at an earlier stage, determining whether an atmosphere still exists and how it is evolving. This initial screening is especially important for planets orbiting red dwarfs. These are the most common stars in the galaxy, and they also make small worlds easier to detect through transits. Many rocky planets within their habitable zones orbit extremely close to their stars and must endure powerful X-rays, ultraviolet radiation, and stellar winds. Before any search for biology can begin, the first question is whether those planets have retained their atmospheres. LHS 1140b helps turn that question into something observable. A large rocky world that has spent billions of years around a red dwarf still leaves a signature from its upper atmosphere. This single case does not show that every similar planet can retain gas, but it proves that a barren outcome is not the only possibility. As more systems are examined, researchers will learn whether LHS 1140b is a rare exception or a member of a much larger group. Cold, massive super-Earths orbiting beyond the hottest regions of red dwarf systems may commonly preserve their atmospheres, or perhaps only worlds that formed with enormous quantities of volatile material can survive the violent youth of their stars. A broader observational sample will help distinguish between these possibilities. The concept of the cosmic shoreline can then be tested with real data. Instead of drawing a boundary based only on planetary mass and radiation, scientists will know which planets truly have atmospheres, which have lost them, and which occupy an uncertain region between the two states. Helium may become one of the markers on that map. Many questions remain unanswered. Does the helium come from the primordial atmosphere or from the planet's interior? Does the outflow change with stellar flares or follow a longer cycle? How thick is the lower atmosphere? Is nitrogen truly its main component? Is there enough carbon dioxide to warm the surface? Or has it accumulated to create extreme pressure? Does water vapor exist in the atmosphere, remain locked beneath ice, or occur only in very small quantities? The surface has not yet revealed its form either. A deep ocean is consistent with the planet's density, but has not been confirmed. A frozen sphere with open water on the dayside remains only a climate scenario. Tidal locking is highly plausible, but has not been directly observed. Layers of high-pressure ice exist in structural models, not in photographs. This long list of questions does not mean science has returned to the beginning. On the contrary, every question is now far more specific than it was when the planet was first discovered. Researchers no longer ask only what kind of world it is. They now know which molecules to measure, which wavelengths to observe, when to observe them, and what kinds of data can distinguish among competing scenarios. That is the value of a small discovery hidden within light. It does not end the investigation. It defines the path forward. Helium directs attention toward the upper atmosphere. James Webb looks deeper for heavier molecules. Ultraviolet observations explain the source of energy. Measurements of mass and radius clarify the interior. Each instrument examines a different layer of the same world. Over the years, those layers may combine into a more complete portrait. The outer region will show gas escaping. The lower atmosphere may reveal its pressure and composition. The surface will be narrowed down among rock, ice, and water. The history of the star will explain how the planet managed to retain its gases. Only then can the question of habitability be placed within a sufficiently deep context. For now, humans have not seen a shoreline on LHS 1140b. No individual cloud has been identified. No ocean has been confirmed. No evidence of organisms has been found. And no combination of gases with biological significance has been detected. Images of dark seas beneath a red star still belong to models and to imagination carefully constrained by data. What has truly reached us is far smaller. A subtle change in the light of a star nearly 49 light-years away. A few wavelengths grow weaker as the planet passes in front. Within that missing light, helium leaves its signature. The signal is small, but its meaning extends beyond a single element. It shows that at least one world larger than Earth, lying within the habitable zone of a red dwarf, has not had its atmosphere completely stripped away by time and radiation. Gravity still holds part of the gas. Another part is escaping, carrying with it the story of a struggle that began when the star system was young. Life remains ahead, beyond the limits of current evidence. There is no scientific reason to say that organisms exist on LHS 1140b. Yet, one of the fundamental conditions that makes such a search meaningful has become clearer. The planet still has an atmosphere, still possesses a system exchanging energy with its star, and still retains enough material for deeper questions to be asked. The coming transits will not immediately reveal oceans or living organisms. They will add only more tiny changes to the starlight. But science rarely advances through a single moment. It advances through repetition, through signatures that are tested, and through possibilities that are eliminated one by one until what remains becomes clear enough to name. LHS 1040. 140b has not told us that life exists elsewhere. It has only shown that the universe still contains worlds capable of holding on to their breath. Sometimes, that is where a true search begins.